Hello there, and welcome to Science for Sleep, where curiosity drifts softly through the quiet corners of thought, and science becomes a gentle way to end the day. Tonight the mind lifts its gaze toward the wide, dark canvas above us. Somewhere out there, beyond the thin air that keeps us breathing, lies the question of distance. Not in the poetic sense, but in the simple, physical way that space itself measures what we can and cannot reach. Every journey begins close to home, even one that stretches into the stars, and ours begins here, in this small moment as you listen. Maybe you're lying in bed, maybe the lights are dim, and maybe there's a window near you with a faint glow of night behind it. Wherever you are, you share the same sky that has quietly waited above humanity, since before there were words to describe it. It's strange to think how recent our steps into space have been. For nearly all of human history, we lived entirely on the surface of this single planet. The sky was a ceiling we could only look at, never touch. The first people who dreamed of flight didn't imagine rockets or satellites. They imagined feathers and wings. Their gaze wasn't yet on other worlds, but on the air itself. For thousands of years, we remained creatures of soil and sea, able to explore only what gravity allowed. That gravity is both our protection and our confinement. It holds us to the Earth's surface, makes rivers flow, keeps the moon circling us, and it's the reason leaving this planet is so hard. To travel anywhere in the universe, we first have to fight against the very thing that keeps us alive. When we think about distance in space, it's easy to underestimate it. The numbers sound abstract, even meaningless. The moon is about 384,000 kilometers away. The sun, about 150 million. Proxima Centauri, the closest star beyond our sun, sits roughly 40 trillion kilometers from here. These are facts that fit on a screen or in a book, but no mind can truly picture them. You could drive for the rest of your life and not make a dent in those numbers. You could fly faster than any plane ever built, and still the darkness ahead would barely shrink. It's the kind of scale that feels more like an idea than a place. Yet, the question tonight is simple, at least on the surface. How far can we travel in space right now? Not in dreams or theories, but in reality, with the engines and materials that exist today. The answer begins close to the ground, at the edge where blue fades into black. That edge, about 100 kilometers above the sea, is known as the Kármán line. It's not a wall or a fixed boundary, it's just the point where the atmosphere becomes too thin for normal flight. Airplanes need air for their wings to push against. Past that line, they can no longer generate lift. Space begins where flight ends. Every rocket we launch must climb through that thin barrier, not to escape Earth's gravity entirely, but to move fast enough sideways that it stays in motion around the planet. Orbit is not so much about going up, as it is about going forward fast enough to keep falling forever without hitting the ground. The first human to do this was Yuri Gagarin in 1961, circling the Earth once before returning safely. He travelled only a few hundred kilometers above the surface, yet that small leap was the first time a human truly left the cradle of the atmosphere. Since then, we've built a steady routine of reaching orbit. Satellites circle overhead by the thousands. The International Space Station glides at about 400 kilometers high, and spacecraft regularly travel back and forth carrying supplies and crews. To an astronaut aboard the station, Earth's surface curves below like a living map. Cities flicker, storms swirl, and sunrise arrives every 90 minutes. It sounds impossibly far, yet in the scale of the solar system, it's barely a whisper away. If Earth were a globe a metre across, the station would hover less than a centimetre above it. That's the first measure of distance in space travel today. We can live and work just beyond the air we breathe, but only by clinging tightly to the planet. To go farther requires speed. The escape velocity from Earth, the speed needed to break free of its gravity completely, is about 11 kilometers per second. Rockets must burn immense amounts of fuel to reach that. Even then, most missions don't go straight out. They spiral upwards slowly, using gravity assists or multiple stages to gain momentum. The most powerful rockets ever built, like the Saturn V or the modern space launch system, can push large payloads toward the moon or beyond. But each additional kilometre per second of speed costs exponentially more fuel. That's the central problem of distance in space travel. Every extra bit of velocity means carrying far more propellant, which itself adds weight, which requires even more fuel. It's a loop that limits how far we can go. For humans, the farthest any of us have travelled remains the moon. Between 1968 and 1972, the Apollo mission sent 24 astronauts there. 12 of them walked on its surface. The distance from Earth to the moon averages about 384,000 kilometres, or roughly 30 times the width of Earth itself. Each journey took about 3 days outbound, 3 days back. That is, in purely physical terms, the edge of our reach. No human has ventured farther in the 50 years since. The moon remains both a destination and a symbol, a silent marker of our current boundary. If you were to travel at the same speed as those Apollo spacecraft, about 39,000 kilometers per hour, it would take you more than 100 days just to reach Mars when it's nearest to Earth. And that's only if the planets are aligned favorably, which happens every 26 months. Even robotic probes, launched with much more efficient trajectories, take 6 to 9 months to reach Mars. The distance fluctuates between 55 million and 400 million kilometers, depending on orbital positions. So while Mars is our next logical target, the scale of that trip compared to the moon is staggering. It's not just farther in distance, but in complexity. Radiation, weightlessness, isolation, and the need for sustained life support turn a few days' flight into a multi-year commitment. Right now, we can send machines much farther than we can send ourselves. The Voyager spacecraft, launched in the late 1970s, are still travelling outward decades later. Voyager 1, the most distant human-made object, has passed beyond the heliopause, the outer limit of the Sun's influence. It's over 24 billion kilometres from Earth, moving at more than 60,000 kilometres per hour, yet it's still within the galaxy, still unimaginably close compared to the stars around us. Its faint radio signals take more than 22 hours to reach us. Each transmission is a whisper from a machine that left before most people alive today were born. To imagine what it would mean for humans to go that far is almost absurd. At Voyager's speed, it would take 70,000 years to reach even the nearest star system. That's longer than the entire span of recorded human history. We can build probes that drift for decades, but we can't yet build ships that sustain life for centuries. Our reach, then, is a gradient. Machines can travel across the solar system. Humans can travel to orbit and to the moon. Everything beyond that remains, for now, beyond us. And yet that limitation doesn't come from lack of imagination. It comes from the mathematics of energy. Chemical rockets, the kind we use now, store only so much thrust per unit of mass. To go faster, we'd need engines that convert mass to energy more efficiently. Ion propulsion systems, nuclear thermal rockets, and proposed fusion drives all promise higher efficiency, but most remain experimental or under development. Even with these, travel to another star would still take generations. That's the scale we're dealing with. Our current tools let us cross the void between Earth and its satellite neighbour, explore nearby planets with unmanned craft, and send a few robotic ambassadors to drift forever into the night. Standing here on the surface of Earth, it's easy to forget that this limitation is not a failure, but a beginning. A few hundred kilometres above us, people float weightless, watching sunrises that come every hour and a half. A few 100,000 kilometres beyond, footprints remain in the lunar dust, untouched by wind or rain. Millions of kilometres beyond that, machines circle other worlds, sending back images of rings, storms, and distant horizons. Billions of kilometres farther, 2 small probes keep moving outward, carrying golden records of sound and music in case anyone someday finds them. That's how far we've travelled, for now. Not yet to the stars, but far enough to know they're waiting. When you step outside and look up, the night seems silent, but it's alive with motion. The space station glides overhead, satellites flash like faint stars, and beyond them, the planets trace their slow orbits around the sun. Light from the moon reaches you in just over a second, from the sun in about 8 minutes, from the nearest star in over 4 years. Those beams of light are the truest travellers we know. They move at the one universal limit, 300,000 kilometres every second, the speed no mass can reach but all light maintains. Every star you see is sending you its own ancient message, the past arriving in the present. That's another way to think about distance, not as meters or miles, but as time. If you could somehow ride one of those photons, the concept of distance would vanish. But since we can't, our journeys remain bound by engines, fuel, and patience. The question of how far we can travel in space right now is as much about our understanding of physics as it is about our place in history. We've only just begun. The technology that lifted us from the ground is less than a century old. The generation that first reached orbit is still remembered by name. The next step, whether to the moon again or to Mars, will extend that story, each mission rewriting what we mean by reachable. The vastness above us isn't empty. It's full of paths not yet taken, each one demanding more energy, more endurance, and more time than the last. And though we can't yet cross the interstellar gulf, every launch, every orbit, every signal that returns from a distant probe pushes our reach a little farther. The silence between worlds is enormous, but it's not impassable. We've already proved that our machines can survive it. The question that remains is when we will go ourselves. As you listen, maybe the quiet around you feels still, but overhead, there are thousands of journeys in progress. The space station continues its endless fall around Earth. Probes circle Mars and Jupiter. Voyager keeps moving outward through the cold. All of it is happening right now, each traveller marking another fraction of a cosmic distance that has no finish line. How far can we travel in space right now? Farther than we ever have, not nearly as far as we dream, and always just a little bit beyond what we thought possible the year before. And so, we keep watching, calculating, building, and imagining. Every step upward begins with looking up. Every meter gained against gravity is a quiet victory over the weight that holds us. From this small blue planet, we've already touched the edge of the infinite. We will keep reaching, because that's what living things do. Long before the first rocket cracked the sky, before the hum of engines or the shimmer of solar panels in orbit, humanity's story of travel began much closer to the ground. It began around fires, under open skies, with people looking outward and wondering what lay beyond the horizon. The need to move, to see, to reach farther, is as old as breath itself. We walked out of forests, crossed rivers, built boats to follow coastlines, and later ships to cross oceans. Each time the unknown felt endless until we found ways to measure it. The story of space travel is not separate from that. It's simply the next long step in a very old pattern. When you think about how far humans can travel, it helps to remember that distance once meant something entirely different. For most of history, the edge of the world was only as far as a person could walk before the sunset. The concept of far away expanded with every invention. The wheel, the sail, the steam engine, each one stretched our reach a little more. The invention of flight changed everything again. The first airplanes carried us above landscapes that had once taken months to cross. When the jet engine arrived, oceans became hours instead of weeks. It's no coincidence that talk of space travel began around the same time. Once the sky stopped being a limit, the idea of leaving Earth became inevitable. But that progression wasn't just about machines. It was about imagination catching up with possibility. A campfire might not seem like the starting point for interplanetary travel, yet that's where the habit of looking outward began. Around those flames, people once stared at the stars and told stories to explain them. Myths of gods, hunters, and travellers filled the constellations. Those stories weren't science, but they kept the stars alive in human thought. Every culture, no matter where or when, built some kind of relationship with the sky. The Egyptians tracked the flooding of the Nile by watching Sirius rise. The Polynesians navigated open ocean by memorizing star positions. Farmers measured seasons by the movement of the sun. Long before we had telescopes, the sky was already a map, a clock, and a mirror of curiosity. What we now call space used to be something holy and unreachable. It wasn't empty darkness. It was a realm of gods and spirits, distant but watchful. To cross into it would have seemed unthinkable. Yet, century by century, that boundary thinned. The invention of the telescope in the early 17th century changed the heavens from myth to landscape. For the first time, the moon wasn't a perfect glowing disk, but a world with mountains and plains. The planets weren't wandering stars but places. The sun had spots, Jupiter had moons, and suddenly the universe looked much more like a neighbourhood than a mystery. Every discovery made the ski less divine and more familiar, and with familiarity came the desire to go there. Even so, the road from that first glimpse through a telescope to an actual flight into space was longer and harder than most people realise. Centuries passed between the first drawings of lunar craters and the first rockets that could reach them. Early thinkers tried to imagine how one might travel upward without falling back down. Some drew cannon-like contraptions, others imagined ladders reaching into the clouds. It all sounds absurd now, but those ideas mattered. They were early sketches of ambition, drawn by people who had no reason to believe such a thing was possible. As the industrial age unfolded, imagination found machinery to match it. Steam power, then electricity, and finally combustion gave humans a level of control over energy that no previous generation had known. In 1903, the Wright brothers flew for just 12 seconds, but those 12 seconds changed the horizon forever. For the first time, humans left the ground not through magic or myth, but through engineering. It's easy to forget how radical that was. For millennia, flight was a dream, a metaphor for freedom or divinity. Suddenly, it was a real experience. The moment we could lift ourselves off the ground, the rest of the universe stopped looking quite so far away. It's worth pausing on that idea. Every new distance reached on Earth redefined what far meant. When humans first crossed the Atlantic, it seemed impossible. When trains connected continents, it became ordinary. The same thing happened with flight. Each new record, higher, faster, farther, reshaped what we believed was within reach. That slow shifting of perspective is what prepared us for space travel. We didn't jump from the ground to the moon overnight. We climbed step by step through centuries of curiosity and risk. By the early 20th century, the language of exploration had turned skyward. Science fiction writers like Jules Verne and H.G. Wells wrote about lunar voyages, Martian civilizations, and interplanetary ships powered by improbable engines. Their stories were still fantasy, but they spoke to something deep and restless in the human mind. They made readers believe that distance, no matter how impossible, was negotiable. And just as myths once helped people imagine the stars, these stories helped inventors imagine the technology to reach them. While writers built dreams, engineers began building machines. Early rocketry experiments in Russia, Germany, and the United States took the first fragile steps towards spaceflight. Konstantin Tsiolkovsky, often called the father of astronautics, wrote that Earth is the cradle of humanity, but one cannot remain in the cradle forever. He calculated the mathematics of escaping Earth's gravity decades before anyone could do it in practice. His ideas were the quiet mathematics beneath what would become the space age. He never saw a rocket fly, but he showed others how it might. That's how humanity moves from hearth to horizon, slowly, then suddenly. We imagine something for centuries, and then one generation decides to make it real. When rockets finally did appear, they began as weapons, not vehicles of exploration. But that's often how human progress unfolds. Our tools of destruction eventually become instruments of discovery. The same technology that launched warheads carried the first satellites into orbit. The same engines that once frightened the world would soon carry humans beyond it. And that brings us closer to understanding our present limits. The idea of distance changed again once the first human left the atmosphere. What had once been infinite became measurable. We could now say, with precision, how far out there really was. The horizon moved from the line of the ocean to the curve of the Earth. The hearth, once a fire in a field, became an entire planet glowing in the dark. For the first time, we saw ourselves from the outside. The famous photographs taken by Apollo astronauts showed Earth as a small sphere suspended in emptiness, fragile, colourful, alive. That image may be one of the most important results of space travel so far. It didn't just show us what we could reach, it reminded us what we already had. From a distance of a few 100,000 kilometres, the divisions and borders that fill our lives disappear. There's only one home visible from there, one fire still burning at the centre of our reach, and yet the human pattern hasn't changed. The same impulse that pushed people to sail past the edge of old maps now drives us to send probes past the edges of our solar system. The methods have changed, but the reasoning hasn't. Curiosity doesn't stop at comfort. Every time we master a horizon, we begin searching for another. So when we talk about how far we can travel in space right now, we're really tracing a much older question. How far can we go before the unknown becomes unreachable again? Each generation redraws that line. For some, it was the other side of a mountain range. For others, the far side of the ocean. For us, it's the space between planets. Our hearth, the place where our stories began, still burns here on Earth. But our horizon has moved beyond air and weather, beyond clouds and storms, into the vacuum that starts just 100 kilometres above us. That shift is both immense and subtle. We're still the same species that once sat by fires and looked up. The difference is that now some of us have looked back down from above. We've extended the boundary of reachable to include orbit and the moon. The next horizon lies at Mars, but the spirit behind it is ancient. The same curiosity that once named constellations now designs flight paths. The same instinct that once followed migrating herds now tracks distant planets. The technology has evolved, but the reason remains unchanged. We explore because we can't seem to stop wondering what's next. Even now, as you listen, that curiosity continues its work. Engineers refine engines, scientists plan missions, and robotic explorers keep moving outward. Our tools reach where we cannot yet follow, but they carry our intentions with them. Each time a probe sends back data from a new distance, we see farther. Each time a rocket launches, the horizon shifts slightly again. From hearth to horizon, from sky to space, from dream to flight, the pattern repeats itself, and somewhere between the warmth of firelight and the cold of the stars lies the present moment, the point where our reach ends for now, but not for long. The distance we've travelled so far is small compared to the scale of the cosmos, but enormous compared to where we began. We've already left the ground, crossed the sky, and touched another world. The rest, as always, will come in time. Above you, the same stars that guided travellers across oceans are still there, their light unchanged. What's different now is that we know how to measure the space between them. We no longer just name constellations, we send instruments to study them. The horizon has become a moving target, a challenge that never ends. The hearth, meanwhile, stays the same, a reminder of where all journeys begin. In that balance between stillness and movement, between home and the unknown, humanity keeps finding its next direction. From the warmth of one world, we reach for others, and as our machines continue outward, Our understanding of distance grows quieter, more precise, and more patient. The horizon waits, as it always has, and we keep walking toward it, one launch at a time. The moment humans first tried to leave the atmosphere wasn't born from wonder alone. It began with calculation, with mathematics written on paper, with engineers building machines that could withstand the unbearable heat and crushing force of launch. The dream of reaching space had lived for centuries, but the reality was mechanical, industrial, and loud. In the early decades of the 20th century, rockets stopped being theoretical. They began to move from drawings into hardware, from imagination into ignition. Those first steps beyond the sky weren't graceful. They were dangerous, clumsy, and often explosive, but they worked. They marked the transition from watching the heavens to touching them. The foundations of modern rocketry were laid by a handful of individuals scattered across the world, working independently yet driven by the same idea. In Germany, Hermann Oberth wrote about the physics of space travel and the use of liquid-fueled rockets. In the United States, Robert Goddard tested small prototypes in empty fields, launching them to modest altitudes and quietly recording the data. In the Soviet Union, Konstantin Tsiolkovsky's equations guided a new generation of engineers who would eventually build the first rockets capable of reaching orbit. These early efforts were limited by the materials and technology of the time, but the principles were sound. Rockets didn't rely on air to push against. They worked by conservation of momentum, expelling mass backward to move forward. That simple concept would one day carry people into orbit, but at the beginning it was just a fragile experiment, one that often ended in failure. World events accelerated the progress. During the Second World War, Germany developed the V-2 missile, the first human-made object to reach the edge of space. It climbed to an altitude of about 180 kilometers before falling back to Earth. It was built as a weapon, a tool of destruction, but it proved that rockets could travel beyond the atmosphere. When the war ended, both the United States and the Soviet Union captured the technology and the scientists who built it. From that point forward, the competition to reach space began not as a peaceful collaboration, but as a race driven by politics and fear. The Cold War turned the idea of spaceflight from dream to necessity. The two superpowers poured immense resources into developing rockets powerful enough to carry not just warheads, but also payloads of scientific equipment. The line between weapon and vehicle blurred. Each nation wanted to prove its technological superiority, and space became the ultimate stage. The irony is that this rivalry, rooted in distrust, produced some of the most extraordinary achievements in exploration. In 1957, the Soviet Union launched Sputnik 1, the first artificial satellite. It was a small metal sphere with 4 antennae, no larger than a beach ball, transmitting a simple radio signal. A steady beep that circled the planet every 96 minutes. That sound, received by amateur radio operators around the world, marked the moment humanity entered the space age. For the first time, something built by human hands was circling Earth in the vacuum beyond air. It was an object from our planet, moving freely in space, and it changed everything. People stepped outside at night, looked up, and realized that one of those faint moving dots was not a star or an airplane, but a machine built on Earth, crossing silently overhead. The launch of Sputnik was a shock to much of the world. It showed that space was no longer unreachable, and that technology had advanced faster than most people realized. Just a month later, the Soviets sent another satellite, Sputnik 2, carrying a passenger, a small dog named Laika. She became the first living creature to orbit Earth, though she did not survive the journey. Her flight demonstrated that life could endure the violence of launch and the conditions of space, at least for a short time. It was both a triumph and a tragedy, but it pushed understanding forward. The United States responded with its own satellite, Explorer 1, launched in early 1958. It discovered the Van Allen radiation belts, regions of charged particles trapped by Earth's magnetic field. This showed that space wasn't an empty void, but an environment with hazards that future astronauts would have to navigate. Every new mission revealed another layer of complexity. Space was not a calm sea waiting to be crossed. It was a region of radiation, vacuum, and temperature extremes. Simply surviving there would require precision beyond anything engineering had attempted before. Within just a few years, the race moved from machines to humans. The Soviet Union once again took the lead. On April 12, 1961, a rocket lifted off from the Baikonur Cosmodrome carrying Yuri Gagarin. He orbited the Earth once, reaching an altitude of about 300 kilometers before re-entering the atmosphere and landing safely. His entire journey lasted less than 2 hours, but it transformed human history. For the first time, a person had travelled beyond the sky and returned to tell the story. The details of that flight are remarkable even today. The capsule, called Vostok 1, was small, barely enough room for Gagarin to sit inside. The control systems were simple, the risks immense. Communication was patchy, and the spacecraft had no way to land softly. Gagarin ejected and parachuted to the ground after re-entry. The mission's success depended on the stability of the rocket, the accuracy of the orbit, and the integrity of the heat shield. Every component worked just well enough. Gagarin's calm voice as he described the view, seeing the curvature of Earth, the thin blue line of atmosphere, became one of the defining moments of the century. The United States soon followed. Less than a month later, Alan Shepard made a suborbital flight aboard a Mercury capsule launched by a Redstone rocket. He reached an altitude of 187 kilometers and landed in the Atlantic Ocean 15 minutes later. It was a short flight compared to Gagarin's orbit, but it proved that America was ready to compete. The Mercury program continued with longer missions, culminating in John Glenn's orbital flight in 1962. For the first time, multiple nations were sending humans into space, and the boundary between sky and cosmos had become a place of competition, experimentation, and cautious optimism. The early astronauts described the same thing in different words. The view from orbit was overwhelming. Earth wasn't flat or infinite. It was small, bright, and fragile. The thinness of the atmosphere struck them. It looked like a delicate film separating life from the blackness beyond. That perspective reshaped not only science, but also human identity. We were no longer confined to the surface. We had become a species that could step outside its planet and look back. At that stage, the distances involved were modest in cosmic terms. The orbiting altitude of a few hundred kilometers is barely above the planet's surface compared to the scale of the solar system. Yet the effort required to reach it was enormous. To place even a small capsule in orbit required a rocket weighing hundreds of tons, burning through stages of fuel in minutes. The difference between falling back to Earth and circling it indefinitely came down to velocity, a precise balance between gravity pulling inward and momentum carrying forward. The margin for error was tiny. Each successful launch built confidence, and each failure taught something new. Rockets exploded, capsules malfunctioned, and yet progress continued. The Gemini program refined techniques like orbital rendezvous, spacewalks, and long-duration missions, all essential for future trips to the moon. Every step beyond the sky added another layer of knowledge about how humans could survive in the harsh environment of space. It was no longer just about reaching orbit. It was about staying there, working there, and returning safely. These first steps were also a test of endurance and trust. The astronauts climbed into machines that had only a brief history of success, sitting atop towers of fuel with no guarantee of return. They accepted the risk because the goal was larger than any individual life. To explore, someone had to go first. The courage required was quiet rather than heroic, a willingness to face uncertainty in the name of understanding. By the mid-1960s, spaceflight had become both routine and extraordinary. Satellites transmitted television signals, weather data, and communications across continents. astronauts orbited for days conducting experiments in weightlessness. Cosmonauts tested new spacecraft designs. The edge of the sky had become a workplace, not just a frontier. The dream that had begun around fires was now a coordinated effort involving thousands of people, from engineers designing circuits to technicians fueling rockets. Humanity had built a small but functional bridge between Earth and the void beyond it. The first steps beyond the sky were not about distance in the grand sense. They were about proof, showing that leaving Earth was possible, that returning was survivable, and that the laws of physics could be mastered enough to make it repeatable. The distance from Earth's surface to orbit may be small compared to the gap between planets, but in human terms it was enormous. It separated all of pre-space flight history from everything that came after. Even now, that boundary remains the hardest part of any journey outward. Reaching orbit still consumes most of the energy of any mission. Once a spacecraft is free of Earth pull, travelling farther becomes easier, but getting there remains the first and most unforgiving step. The early spacefarers learned that lesson through experience and precision, through trial, and often through failure. When you look up at the night sky and see a satellite drift across it, you're watching the result of that long, dangerous learning process. Every glint of light moving silently above is a descendant of those first fragile machines that broke the atmosphere half a century ago. Each orbit traces a line of progress, a reminder of how far we've come since the first person imagined leaving the ground. The sky no longer ends where it used to. The edge has moved upward, outward, and continues to move still. Those first steps may seem small now, measured in kilometres, but they mark the beginning of a new scale of travel, a scale measured not by geography, but by gravity. And even as new generations plan journeys to the Moon and Mars, the first steps beyond the sky remain the foundation. They were the proof that leaving was possible and that coming back was worth the risk. The engines that carried those first explorers burned for only a few minutes, but the momentum they created has never stopped. Each rocket launch since carries not only its payload, but the accumulated courage and precision of everyone who built, studied, and dared before. The sky that once felt infinite has become a starting line, and everything beyond it now waits for the next climb. When the first astronauts left Earth, they didn't go far, but they crossed a boundary that had never been crossed before. It's difficult to describe the difference between staying here and leaving, because the numbers sound small. A few hundred kilometres straight up, that's all. You could drive that distance in a few hours, but vertically it's a journey through everything that sustains life into a place that cannot. The moment a spacecraft rises past the last traces of atmosphere, it enters a region where air, pressure, and temperature no longer behave the way they do down here. Beyond that invisible line, survival depends entirely on what you bring with you. The early missions that left Earth didn't stay away for long, but they taught us everything about how to go farther. Those first departures were short, tense, and filled with uncertainty. The rockets that carried people beyond the atmosphere were still new inventions, each launch a test as much as a mission. In the United States, the Mercury and Gemini programs served as the steps between the first experiments and the later lunar attempts. Mercury proved that a human could survive the violence of launch, the emptiness of space, and the heat of re-entry. Gemini proved that humans could live in orbit for days, move between spacecraft and return with precision. Each mission had clear, measurable objectives: test a system, refine a procedure, confirm a theory. Behind every flight were thousands of engineers, scientists, and technicians trying to solve problems that had never existed before. For the astronauts, leaving Earth meant something both physical and psychological. During ascent, the body experienced several times the force of gravity pressing it into the seat. The vibration shook through every muscle and bone. The sound inside the capsule was not like thunder or wind, but a continuous roar of machinery working at its limits. Then suddenly silence. Weightlessness began not with a sense of floating, but with the absence of weight entirely. Objects that had been fixed in place now drifted. Hands that had pushed against controls now moved freely. For the first time, humans experienced what it meant to be unanchored from the planet. Outside the window, Earth filled the view. No horizon, no division between ground and sky, just the curve of a sphere surrounded by darkness. From orbit, the planet doesn't look infinite. It looks contained, alive, and delicate. The first astronauts described the colour more than anything else. They expected grey or white clouds, but what they saw was deep blue water and bright landforms. The atmosphere appeared as a thin glowing line, almost translucent. That line, only a few dozen kilometres thick, was the boundary between everything we know and everything beyond. To see it from above was to realise how narrow the margin of safety really is. Each orbit around Earth takes roughly 90 minutes. In that time, an astronaut passes from daylight to night and back again. Sunsets and sunrises follow one another so quickly that the rhythm of time loses its normal meaning. Sleep cycles must be scheduled artificially, meals are measured, and even basic movement requires adaptation. Every action in microgravity takes more effort to control. A simple motion, like turning a wrench or pouring a drink, becomes a process of managing equal and opposite reactions. Muscles weaken, fluids shift within the body, and the inner ear loses its sense of up and down. For short missions, these changes are temporary, but they hint at how fragile our biology is when detached from gravity. Despite the challenges, leaving Earth for even a brief time showed how resilient humans could be. The Gemini missions in the mid-1960s extended flight durations to nearly 2 weeks, proving that people could live and work in space without losing mental or physical function. They practiced docking 2 spacecraft together, a maneuver essential for lunar missions. They conducted the first spacewalks, stepping outside their capsules into open vacuum, tethered only by cables and faith in engineering. These were moments of trial as much as triumph. On his first spacewalk, astronaut Ed White floated for 20 minutes and described it as the most exhilarating experience of his life. Yet, he also learned how easily motion could become uncontrollable without air resistance or gravity. Every movement required precision, every breath measured. As engineers refined the spacecraft, the missions grew in complexity. They learned to control re-entry trajectories, to manage life support systems, to handle emergencies without immediate assistance from Earth. Each launch added another piece to the puzzle of how to leave Earth safely and return. The margin for error remained small, but confidence grew. The astronauts weren't just passengers, they were test pilots in environments where no human intuition could fully apply. Their senses had to adjust to new realities. The absence of sound transmission through air, the constant spin of the planet beneath them, the subtle pull of acceleration that replaced gravity for moments at a time. Leaving Earth was never meant to be a permanent act, not yet. These early missions were built on the assumption of return. Every spacecraft launched during that era was designed to come home. Even as astronauts orbited the planet, their connection to the ground remained absolute. Mission Control monitored every heartbeat, every valve, every flicker of power. Communication lines stayed open, and ground crews followed every orbit in real time. In that sense, leaving Earth was less about escape and more about extension, stretching the boundaries of presence while maintaining a thread of contact. Each time a capsule re-entered the atmosphere, it faced conditions far harsher than launch. Friction turned speed into heat, thousands of degrees hotter than any metal could endure without protection. The heat shield ablated, burning away layer by layer, carrying the energy off in vapor and plasma. From the ground, the returning spacecraft appeared as a streak of light across the sky. Inside, the crew felt gravity return like a heavy blanket, pressing them down after hours or days of weightlessness. The parachutes deployed, the descent slowed, and the ocean or the steppe rose to meet them. The moment the capsule hit water or land, the mission became memory. The astronauts were back on the only planet they knew how to live on, and yet they would never see it the same way again. For most of human history, the idea of leaving Earth was a metaphor, something reserved for gods or dreams. In the span of a single decade, it became a technical procedure. By the late 1960s, launch windows, orbital mechanics, and re-entry profiles were standard terms. Spaceflight became a process that could be calculated, rehearsed, and repeated. But repetition didn't make it ordinary. Every mission carried the weight of risk, the awareness that a single malfunction could turn a journey outward into a catastrophe. Engineers worked relentlessly to reduce that risk, to turn each new departure into something a little safer than the one before. The first people to leave Earth returned with something invisible but lasting. They carried perspective. From above, there are no borders, no divisions, no lines separating one country from another. There is only one planet, one layer of air, one surface connecting everything. That view changed not just how astronauts saw the world, but how everyone else imagined it. Photographs from orbit began appearing in newspapers and magazines. The public saw what Earth looked like as a whole, and it inspired a sense of both pride and responsibility. The environmental movement, the awareness of planetary limits, even the phrase "spaceship Earth" emerged from that imagery. Leaving Earth, even briefly, made us understand home in a new way. When Apollo missions began, those lessons from Mercury and Gemini formed the foundation. By then, engineers knew how to launch, how to orbit, and how to bring people back alive. What remained was distance. The Moon waited as the next destination, farther than any spacecraft carrying humans had ever gone. But every minute spent in orbit, every test flight, every controlled landing was practice for that greater leap. Leaving Earth, even for a few hours, had shown that the human body could survive the transition from gravity to weightlessness and back again. It proved that the boundaries of life could be stretched without breaking. To step beyond the atmosphere, even for a short time, is to touch a kind of silence that doesn't exist anywhere on the planet. There's no wind, no sound, no scent, only the mechanical hum of systems keeping you alive. That silence is not empty. It's dense, filled with the awareness that beyond your spacecraft there is nothing but vacuum. Astronauts often describe how that emptiness sharpens their sense of connection to Earth. They can see the entire planet at once, but cannot reach it. The distance may be small, but the separation feels immense. In that sense, leaving Earth briefly isn't just a technological event, it's an encounter with scale. From orbit, every mountain, ocean and city shrinks into a single pattern of light and shadow. The realization that all human life happens within that narrow band of colour and weather is overwhelming. Many astronauts have said that the hardest part of spaceflight isn't the launch or the landing, but the return. The adjustment to the idea that you've seen everything at once and must now focus again on one small part of it. Those brief journeys created a bridge between the familiar and the infinite. They were tests of endurance, proof of concept, and glimpses of what lay ahead. Each successful orbit marked another confirmation that humans could exist, however temporarily, outside the environment that shaped them. From those experiences came the confidence to plan missions that would last weeks, then months, then eventually years aboard space stations. Leaving Earth, even for a short time, didn't mean abandoning it. It meant seeing it clearly for the first time. The people who went up and returned carried back not just data but perspective, not just experience but humility. They had been somewhere that no human body was meant to go, and they survived because of precision, cooperation, and trust in the systems that supported them. And though they only went a few hundred kilometers away, that was enough to change everything. Those few hours or days in orbit proved that travel beyond Earth wasn't science fiction anymore. It was a process we could repeat, improve, and build upon. The next steps, journeys to the Moon, the construction of stations, the dreams of Mars, would all depend on what was learned in those early brief escapes. The sky had been crossed, the planet had been left. Even for a moment humanity had become a spacefaring species, and there was no turning back. The idea of leaving Earth may seem ordinary now, almost routine in headlines or broadcasts, but it remains one of the rarest human experiences. Only a few hundred people have done it, and each one describes it differently, yet their stories share the same core, the realization that distance changes perception. To look down on the world is to see it whole, fragile and finite. That view reshapes what it means to live here. Every launch that follows still carries that echo. Each rocket that rises into the sky traces the same path carved by those first missions. The flames and thunder of departure give way to quiet and weightlessness. The destination may change, low Earth orbit, lunar orbit, or beyond, but the act is the same. Leaving Earth, even briefly, is still the threshold between all that is known and all that remains to be explored. When the first space station was launched, it wasn't just another experiment in engineering. It was an announcement that humans could build a home in a place that had no air, no ground, and no natural shelter. Until then, every journey into orbit had been a visit, a short trip outward, followed by a quick return. But the creation of an orbital home changed that. It meant that people could live, work, and sleep off the surface of Earth for weeks, then months, and eventually years. It was no longer a matter of reaching space, it was a matter of staying there. The idea of a station circling Earth didn't appear suddenly. It was the natural next step after the first orbital flights. As soon as engineers knew that a human could survive in orbit, they began imagining ways to make it last longer. Early capsules were small, cramped, and offered almost no room to move. The longest Gemini missions lasted just under 2 weeks, and by the end, the astronauts felt the physical strain of confinement. For spaceflight to become sustainable, there had to be more room, more comfort, and better systems to recycle air, water, and power. Living in orbit required turning an environment of survival into one of endurance. The first real attempt came from the Soviet Union in 1971 with the launch of Salyut 1. It looked simple, a long cylinder with solar panels, but it represented something monumental. It was the first human-made habitat in space, the first place designed for continuous living beyond Earth. A crew of 3 cosmonauts boarded the station and spent 23 days conducting experiments and testing life support systems. The mission ended in tragedy when their capsule depressurized during re-entry, but the data gathered proved that extended stays in orbit were possible. The idea of an orbital home didn't die with them. It became a goal to refine and perfect. Over the following decade, both the Soviet Union and the United States built and tested several stations. The Americans launched Skylab in 1973, repurposing parts of a Saturn V rocket to create a space habitat large enough for movement and real work. Astronauts spent months aboard, growing accustomed to weightlessness, observing solar activity, and learning how the human body adapts to long-term space living. Skylab demonstrated that humans could live in orbit for extended periods without severe health consequences, though it also exposed new challenges. Muscles weakened, bones lost density, and even simple tasks required careful adaptation. When it re-entered the atmosphere in 1979, it burned up, scattering debris over the Indian Ocean and Western Australia. But its legacy was foundational. Meanwhile, the Soviets continued developing a series of increasingly sophisticated Salyut stations, each one staying longer, carrying more crew, and performing more complex missions. By the 1980s, their program culminated in Mir, a modular space station that became the first true long-term orbital home. Mir stayed aloft for 15 years, hosting astronauts from around the world. It was often compared to a science laboratory, but in reality it was closer to a frontier outpost. Cramped, noisy, occasionally malfunctioning, yet functional. Life aboard Mir meant adjusting to a constant hum of machinery, narrow sleeping areas, and the awareness that outside those thin metal walls was absolute vacuum. It wasn't comfortable by earthly standards, but it was stable enough to call home. Life on Mir revealed what living in space really meant. The rhythm of daily activity followed a schedule designed to mimic Earth time. Crews woke, exercised, ate, worked, and slept in 6-hour blocks to keep their circadian rhythm aligned. Meals came in vacuum-sealed packets, rehydrated with hot water. Showers were rare and complicated, using wipes and minimal water. Exercise wasn't optional. It was mandatory to maintain muscle and bone strength. Without gravity, the human body begins to weaken almost immediately. Every day spent in orbit required countermeasures to preserve what gravity on Earth provides automatically. Communication with mission control provided constant connection, though signals sometimes lagged or dropped. The psychological strain of isolation and confinement became a major field of study. Living in orbit wasn't just a physical test, it was a social and emotional one. Crews had to manage stress, boredom, and interpersonal dynamics in a place where privacy barely existed. There were disagreements, fatigue, and moments of frustration, but there were also routines that stabilized life. Reading, music, brief video calls with family, and the simple ritual of looking out the window at the planet below. That view never lost its power. To live on an orbital station is to see the world as a living map. From that vantage, the curve of the Earth fills every window. Sunlight reflects off oceans. Storms swirl in slow spirals, and lightning flashes across entire continents. The night side of the planet glows with city lights and auroras. Every 90 minutes the station circles the globe, passing through 16 sunrises and sunsets each day. There's no up or down, only directions relative to the structure itself. Astronauts learn to orient by habit rather than gravity. Over time, their movements become effortless, each push and turn calibrated to avoid collision in the tight quarters. The sound inside a station is constant. Fans circulate air, pumps move fluids, and computers hum softly. Silence would mean failure, because silence would mean the systems have stopped. Sleep happens in small compartments with straps to keep the crew from drifting. The darkness of space is absolute, but the station itself never stays still. It glides endlessly around the world below, a home in motion. After Mir, the next great leap came with the International Space Station, or ISS. Built as a collaboration between nations that had once competed fiercely in the space race, it became a shared platform for science and human presence in orbit. The first module launched in 1998, and for over 2 decades it has remained continuously inhabited. More than 270 people from 20 countries have lived and worked there, making it one of the most significant achievements in human engineering. The ISS is not a single structure, but a collection of interconnected modules, each built for a specific purpose. Laboratories, living quarters, docking ports, storage areas. Together they form a home roughly the size of a football field, orbiting at an altitude of about 400 kilometers. The life inside hasn't changed in essence from Mir, but technology has made it more reliable. The station systems recycle most of its water, filter its air, and generate oxygen from electrolysis. Solar panels stretch across its frame, converting sunlight into power. It's a delicate balance of inputs and outputs, constantly monitored from Earth. The ISS circles the planet every hour and a half at 28,000 kilometers per hour, and yet inside, daily life feels almost calm. Crew members conduct experiments in biology, physics, and medicine. They test materials and study how fluids behave without gravity. Every action contributes to understanding how humans might live farther from Earth, on the Moon, on Mars, or in deep space. Still, even with all that progress, the ISS remains a fragile island. It depends entirely on resupply missions for food, equipment, and replacement parts. Waste must be carefully stored or loaded onto returning cargo ships. There's no self-sufficiency yet, no closed system that could last indefinitely. life in orbit remains an exercise in maintenance and vigilance. The station is robust, but it's also temporary. Its components age, and one day it will be replaced by newer structures. Yet while it lasts, it serves as humanity's permanent outpost above the planet, proof that our species can sustain life in a place that offers none. What's striking about living in orbit is how quickly the extraordinary becomes normal. New crew members arrive wide-eyed, overwhelmed by the view and the sensation of floating. Within days, they begin moving gracefully, managing experiments, fixing systems, and communicating with ground control. The novelty fades, replaced by routine. But there's one thing no one seems to get used to: looking down. Seeing Earth from that perspective changes something fundamental. It's not just the beauty of the view, it's the realization that everything you've ever known fits inside that sphere. Astronauts often describe it as a moment of perspective that words can't fully capture. The vastness of space doesn't make Earth feel small, it makes it feel singular, the only place in reach that holds life. An orbital home is not comfortable by any usual measure. There's no weather, no natural sound, no fresh air. Every bit of it is artificial. But within that controlled environment, humans have found a way to adapt, to create routines that feel familiar. There's coffee in the morning, laughter during shared meals, quiet during work, and even time for celebration. Birthdays, holidays, and national milestones are observed with simple gestures, a recorded message, a floating flag, a moment of connection with those below. In its own way, the ISS mirrors life on Earth, just condensed into a few rooms suspended above it. The people aboard the station serve not only as researchers, but as caretakers of a fragile bridge between worlds. They maintain a constant presence in space so that humanity doesn't lose its foothold there. Every orbit reaffirms that we can live away from the planet, if only temporarily. The knowledge gained from this orbital home lays the groundwork for the next step: habitats beyond Earth's gravity, perhaps on the Moon or Mars. Each experiment, each routine maintenance task, each successful day aboard adds another piece to that future. What began as a contest between nations has become a shared human endeavour. The ISS carries no borders. Its components come from Russia, the United States, Europe, Japan and Canada. Crews train in multiple languages, operate mixed systems, and rely on international cooperation for survival. In orbit, national identity fades. Teamwork replaces rivalry. The home that orbits above Earth represents not just scientific progress, but a model of what long-term exploration might require: collaboration, patience, and mutual dependence. Even after more than 2 decades of continuous operation, the station still inspires awe. When it passes overhead, visible from the ground as a bright moving light, it's easy to forget what that point of light contains. Inside, people are working, eating, and sleeping as the world spins below them. They see continents drift into view, storms bloom and fade, cities glow through the night. Every orbit is a reminder of how connected life on Earth truly is, and how fragile our presence in space remains. A home that orbits may sound simple, but it's one of humanity's most complex achievements. It's the balance of technology and trust, of distance and connection. The people who live there do so not for comfort but for discovery, not for isolation but for understanding. They are part of a long chain of explorers whose reach extends a little farther with each generation. From the ground, the ISS looks like a single bright dot. From inside, Earth looks like everything. Between those two perspectives lies the truth of our current reach. We have not yet travelled to the stars or colonised other worlds, but we have built a place to live in the void, a place that circles endlessly, reminding us that exploration doesn't always mean leaving home behind. Sometimes it means carrying a small piece of it with you, keeping it alive, even as it floats 400 kilometres above the surface, endlessly moving, endlessly circling, waiting for the next step outward. The farthest any human has ever travelled from Earth is about 384,000 kilometres, the average distance to the Moon. It doesn't sound like much when compared to the billions of kilometers our probes have crossed, or the trillions that separate us from other stars. But for our species, bound by gravity, dependent on air, and made to live in one narrow shell of temperature and pressure, it is an almost impossible achievement. The edge of human reach is defined by where we have actually been, not where we hope to go, and right now that boundary lies at the moon. That distance was crossed half a century ago, during a brief and extraordinary chapter of history. Between 1968 and 1972, the Apollo missions carried 24 astronauts to the moon, 12 of whom walked on its surface. The journey began with a roar of engines and ended in silence, on a world with no air and no sound. In the space of 4 years, humanity leapt farther than it ever had before, and has not gone farther since. The path to that moment was neither smooth nor guaranteed. The Apollo program grew out of the urgency of the Cold War, a competition that turned exploration into a demonstration of capability. Yet the result was something far greater than politics. It forced human ingenuity to meet the most difficult problem imaginable: how to send life into an environment where nothing alive had ever existed, and how to bring it back. The complexity of that challenge created an infrastructure of science and engineering that continues to shape spaceflight today. To reach the moon, a spacecraft must first escape Earth's gravity well. That means reaching at least 11 kilometers per second, roughly 33 times the speed of sound. The Saturn V rocket that made it possible stood taller than a 30-story building and produced more thrust than any machine ever built. It was designed not as a weapon, but as a transport system for survival. Every stage burned for minutes, shedding weight and increasing speed until the remaining third stage engine pushed the Apollo spacecraft onto a trajectory toward the moon. Once that final engine shut down, the astronauts were no longer orbiting Earth. They were falling toward another world. For 3 days they travelled through open space, far beyond the protective magnetosphere that shields Earth from radiation. In that void, distance became a new kind of reality. The Earth shrank behind them, transforming from a globe to a crescent to a pale sphere no larger than a fingertip. The moon, at first invisible, grew steadily until it filled the windows. Inside their small capsule, the astronauts could see both worlds at once. One a living planet wrapped in clouds, the other a dead rock reflecting sunlight. Between them stretched a silence that no one had ever crossed before. The first time a human saw the moon up close was during Apollo 8 in December 1968. It didn't land, but it orbited, taking photographs and mapping the surface. From that mission came one of the most influential images ever taken, Earthrise, showing the blue planet rising above the lunar horizon. It was a view no human had ever seen, and it revealed something essential. From that distance, the entire planet looked fragile, singular, and borderless. The astronauts' words were plain and factual, but the picture itself carried a quiet message: that our world is small, connected, and finite. When Apollo 11 landed in July 1969, the achievement wasn't measured just in distance, but in precision. Landing on the moon required timing so exact that even a few seconds' error could mean missing the surface entirely. The lunar module, Eagle, descended on a controlled engine burn, guided partly by computers and partly by manual correction from Neil Armstrong. The landing site was rougher than expected, filled with rocks and craters. With fuel running low, Armstrong took manual control and steered the craft to safety. When it touched down, only seconds of fuel remained. The message he sent, "The Eagle has landed," was the confirmation of a feat that had seemed impossible a decade earlier. The moon's surface offered no comfort. The sky was black, the ground grey and dusty, and the sunlight harsh. The temperature swung from freezing to boiling depending on the angle of light. There was no sound except for the faint hum of machinery through the astronauts' suits. Walking there was like moving inside a slow-motion dream, every step exaggerated by the lack of gravity. The dust clung to everything, sharp and metallic smelling. Yet, amid that alien landscape, the astronauts performed tasks as ordinary as setting up instruments, collecting rocks, and taking photographs. They left footprints that, even now, remain unchanged. There is no wind on the moon to erase them. The farthest humans have ever been from Earth was during Apollo 13, when the spacecraft swung around the far side of the moon on a trajectory that placed its crew roughly 400,000 kilometers from home. At that distance, Earth was just a bright point suspended in darkness. The mission had suffered an explosion that crippled its systems, and the crew survived only by rationing power, oxygen and water, while engineers on the ground improvised solutions. Their safe return was one of the most dramatic rescues in history, and it underscored how fragile every journey beyond the planet truly is. For all the grandeur of those missions, they were short. Each lasted just over a week. The astronauts spent no more than 3 days on the lunar surface before returning to orbit, rejoining the command module, and beginning the trip home. Once the final Apollo mission, Apollo 17, ended in December 1972, humanity's physical boundary retreated. Since then, no person has travelled beyond low Earth orbit, a distance of only a few hundred kilometres. We built a permanent presence there with space stations, but the deep space frontier has remained untouched by human hands for over 50 years. The reasons for that pause are practical as much as political. The cost of sending humans to the moon was immense. Each launch required thousands of workers, countless components, and years of planning. The risks were extreme, the returns uncertain. After the initial goals were met, priorities shifted. Robotic exploration could achieve more science at lower cost, and attention turned to building sustainable systems in orbit. Yet the legacy of those lunar missions never faded. They proved that leaving Earth's gravity well was possible. They defined the limits of our current reach, and gave us the data to understand what it would take to go farther. The edge of human reach is not fixed. It's a point in time defined by technology, willpower, and risk tolerance. In the 1960s, that edge moved from the atmosphere to the moon in less than a decade. Since then, it has held steady, not because we can't go farther, but because we haven't yet built the systems to make it safe and sustainable. The moon remains both a milestone and a mirror. It shows us how far we came in one burst of effort, and how long we've stayed in orbit since. Even today, when astronauts aboard the International Space Station look out at the moon, they see the farthest place their predecessors have walked. It's visible from their windows every few hours, depending on the orbit, a constant reminder of distance measured not in kilometres but in human effort. The gap between orbit and the moon may seem small on a chart, but in reality, it's the difference between a short commute and an interplanetary voyage. To cross it again requires not just rockets, but life support systems that can last for months, radiation shielding that can endure solar storms, and propulsion that can carry heavy cargo safely. The new generation of lunar missions aims to move that boundary again. Projects like NASA's Artemis program, as well as international and private efforts, plan to return humans to the moon and build sustainable bases there. Unlike Apollo, these missions are not meant to be brief visits. They are designed to prepare for journeys farther out, to Mars, to asteroids, to deeper space. The moon, once the outer edge, may soon become a waypoint, but as of now it still marks the limit of where human footprints exist. When you look up at the moon from Earth, you're seeing a place that once held human presence but hasn't since. It's both familiar and distant, visible to everyone yet visited by only a few. The time between those landings and today has stretched long enough for an entire generation to grow up knowing that we once went there but not remembering it firsthand. That gap between what we achieved and what we maintain defines the present boundary of human exploration. The edge of human reach is more than a measure of distance, it's a measure of commitment. Going beyond requires more than technology. It requires a sustained decision to keep going, even when the novelty fades. We have the knowledge, the tools, and the ambition, But what limits us now is endurance. Reaching the moon once was an extraordinary feat. Staying beyond Earth for generations will be a transformation. Still, that earlier achievement remains unmatched in scale. Every astronaut who has travelled to the moon carries the experience of seeing both Earth and the moon in the same frame. One bright, one grey, both suspended in black. That sight remains one of the most profound ever witnessed by a human being. From that distance, the planet looks peaceful, unified, and small enough to cover with a thumb. It's a view that compresses all of human history into a single glowing sphere. No photograph or recording can truly convey what that must have felt like. To be held by nothing but a thin layer of metal, to drift in a place where silence is absolute, and to know that the line between safety and infinity is thinner than a wall. That is the edge of human reach. Not a number, not a record, but a fragile point where life meets the void and manages, for a brief time, to endure. Until we go farther, that edge remains unchanged. It sits quietly in the distance, a half-lit reminder of what is possible when determination outweighs fear. We know what it takes to return there. We know how much risk it demands. And still, we look up, tracing the faint boundary between what we have done and what waits ahead, aware that every orbit, every experiment, every launch we conduct brings us a fraction closer to crossing it once again. When the last Apollo mission returned to Earth in December 1972, the engines went silent, and for the first time in over a decade, humanity stopped travelling farther. The astronauts splashed down in the Pacific, the command module bobbed in the waves, and the space program that had sent humans across nearly 400,000 kilometres of emptiness quietly came to an end. The flags were packed away, the rockets dismantled or stored in museums, and the launch pads that had thundered through the 60s and early 70s grew still. The great leap outward had been made, and then, almost immediately, we stopped. What followed was not failure, but pause. A long, slow stretch of time where our ambitions turned inward, and space became something we visited rather than explored. At first, many believed the break would be temporary. The technologies existed. The spacecraft designs could be refined. Plans for Mars missions were drawn up as early as the mid-1970s, and some engineers expected humans would reach the Red Planet by the end of the century. But the world that had driven Apollo forward was changing. The race that had made space a matter of national urgency no longer existed. The Cold War was still ongoing, but the symbolic victory of the moon landing had already been won. The political fuel that powered those massive rockets was exhausted. Without it, there was no longer a clear reason to spend so much so fast for destinations so far away. The 1970s marked the beginning of a more cautious era. Budgets tightened, priorities shifted, and the vision of routine deep space travel gave way to the reality of maintaining a foothold close to home. The Apollo program had cost roughly 4% of the entire US federal budget at its peak. No other national effort outside of war had ever commanded so much money, manpower, and attention. Once the initial goals were met, sustaining that level of investment became politically impossible. Public interest faded. The world's problems, energy crises, inflation, wars, environmental change were close, visible, and urgent. The distant, silent moon seemed less pressing. But the pause wasn't just financial or political, it was technological. The spacecraft that carried astronauts to the moon were built for short-term missions. They were fragile, single-use vehicles designed for one destination. The systems that sustained life, guided navigation, and provided power were all made for journeys measured in days, not months or years. To go farther, to Mars or beyond, would require entirely new engineering, long-duration habitats, reliable propulsion, radiation shielding and life support systems that could sustain humans without constant resupply. The technology to do that simply didn't exist yet. The moon was reachable, everything beyond it was not. at least not safely, so humanity redirected its efforts toward learning how to live in space for longer periods, not by going farther, but by staying up. The 1970s and 80s became the age of stations. First came Skylab, a converted rocket stage that served as America's first space habitat. Then the Soviets launched the Salyut stations and eventually Mir. Each of these orbiting homes taught lessons about endurance, resource recycling, and the toll of weightlessness. The focus had shifted from distance to duration. The challenge was no longer getting to a destination, but learning how to exist away from Earth without breaking down. In that sense, the long pause wasn't a stop so much as a change in direction. It was a retreat from bold expansion into careful preparation. We learned how the human body responds to months in microgravity, the loss of muscle and bone, the shifting of fluids toward the head, the subtle effects on vision and balance. We studied how to grow plants in closed systems, how to filter air and water, how to fix machines that can't be replaced. The work was quieter, slower, less dramatic than the moon landings, but in many ways more important. Without that period of learning, the next steps, to the moon again, to Mars, would be impossible. Still, for decades, no one went beyond low Earth orbit. The farthest any human travelled after Apollo 17 was about 600 kilometres, a distance so small compared to the lunar journeys that it barely registered on the same scale. The shuttles, introduced in the 1980s, were designed to operate near Earth. They carried satellites, built the International Space Station, and provided a reusable way to access orbit, but they were never meant for interplanetary travel. Their range ended where the atmosphere fades into vacuum. The shuttle era was one of repetition and refinement. It turned spaceflight into something almost routine, but it also confined it. We became visitors to space, not explorers of it. There were moments when it seemed like we might break free again. In 1989, President George H.W. Bush announced the Space Exploration Initiative, which aimed to return humans to the moon and eventually send them to Mars. The plan estimated a 30-year timeline and a cost exceeding $500 billion. It never progressed beyond paper. Later efforts, NASA's Constellation program in the 2000s, Artemis in the 2020s, would revisit the same ambitions, each time meeting new challenges of budget, technology, and global priorities. Every generation seems to rediscover the dream, move toward it for a while, then slow down again. For the engineers who kept working through those quiet decades, progress was measured differently. They weren't chasing headlines or historical firsts. They were building reliability. They developed materials that could withstand radiation longer, computers that could operate autonomously, and propulsion systems that used fuel more efficiently. Robotic missions took the lead. Voyager, Pioneer, Viking, and later Cassini, Galileo, and New Horizons all travelled where humans could not. They became our proxies, extending our senses into the outer planets and beyond. These machines carried pieces of us, symbols, messages, instruments, sent back information that deepened our understanding of the solar system. That was the paradox of the long pause. Even as human travel stopped expanding outward, our robotic presence grew faster than ever. The same decades that saw no human leave low Earth orbit saw probes land on Mars, descend into the clouds of Venus, skim the rings of Saturn, and fly past Pluto. While people stayed home, our machines explored the solar system in our place. We learned more about distant worlds than ever before, but we did it from afar. The human body remained bound by gravity, but the human mind kept moving outward through circuits, radio waves, and distant signals. Culturally, the moon faded from memory and became nostalgia. The first generation to see humans walk on another world grew older, and those who followed knew it only as history. The footage of Apollo, the grainy steps, the flags, the dust, became symbols of a time that seemed impossibly ambitious. The space race era began to look like an anomaly, a flash of focus unlikely to be repeated. What was once the frontier became myth. Yet beneath that stillness, something essential was happening. The pause allowed reflection. It gave scientists time to understand what long-term exploration really requires, not just speed and power, but patience, precision, and sustainability. Apollo had been a sprint. The next era would need to be a marathon. The time between the last lunar landing and the next attempt to go back is longer than the time between the Wright brothers' first flight and the Apollo 11 mission. But that span is filled with continuous learning. The long pause also changed the way humanity thought about space. It was no longer just a place to conquer, but an environment to understand. The emphasis moved from flags to science, from records to research. The International Space Station, first assembled in 1998, became the living embodiment of that shift, a collaboration among nations that had once competed to reach space first. Instead of racing each other to distant worlds, they began working together to survive off-world for extended periods. That collaboration became one of the most enduring aspects of the post-Apollo era. Even as rockets stood silent between launches, the dream never truly stopped. It just slowed, reoriented, matured. The new generation of scientists and engineers grew up with a different vision, one of sustainability, reusability, and cooperation. They built rockets that could land themselves, spacecraft that could operate autonomously, and habitats that could recycle their own resources. The technology we have now, reusable boosters, advanced life support systems, plans for lunar bases, all grew out of the lessons learned during the decades when we stayed close to home. To many, the long pause feels like lost time, a half-century in which we could have gone farther but didn't. But distance alone doesn't measure progress. The ability to go far means little if we can't stay there safely. The moon taught us how to reach another world. The pause taught us how to survive away from our own. The combination of those two lessons is what will eventually carry us beyond both. Even now, as new rockets rise and new plans take shape, the stillness of those years remains part of the story. It's the space between two great movements, one that reached the moon and another that will someday reach beyond it. Every long silence in exploration carries a purpose. It's the breath before the next step, the recalibration between leaps. Humanity may have paused at the edge of the moon, but that pause has been the foundation for everything to come. When the next astronauts leave Earth's orbit again, their path will depend on everything learned during those quiet decades. The physics of living in zero gravity, the chemistry of recycling air, the psychology of isolation, the economics of cooperation. The long pause was never a retreat, it was preparation. It's what turned a moment of exploration into a future of endurance. Now, as the rockets once again ignite and the moon missions return to planning stages, we can see the pattern clearly. Exploration moves in cycles: burst, reflection, and renewal. The distance may not have changed for 50 years, but the readiness has. The long pause is ending not because ambition returned, but because the time spent waiting was not wasted. We built knowledge in the stillness. We learned to live above Earth before we tried to live beyond it. And soon, perhaps very soon, the silence between the planets will carry human voices again, crossing the same emptiness that once seemed final, turning the long pause into the start of another great climb. Before humans could think about going farther again, our machines had already left us behind. While the space stations orbited close to Earth and astronauts continued their short cycles of arrival and return, another kind of traveller began to push the frontier outward, one that needed no air, no food, and no rest. These were the robotic explorers, machines built to go where human bodies could not yet survive, to travel for years or even decades through vacuum and radiation, gathering knowledge on our behalf. They became our eyes and instruments in the deep dark. In a sense, they are the true pioneers of the space age, the silent emissaries that have gone far beyond the reach of life. The story of our robotic exploration began alongside human spaceflight, not after it. Even before the first astronaut entered orbit, uncrewed probes had already reached space. The earliest missions were simple, designed to measure radiation levels, cosmic rays, and micrometeoroids, the environment through which future humans would travel. But it didn't take long for those early machines to aim higher. Once we learned to escape Earth's gravity, we began sending probes toward other worlds. In 1959, the Soviet spacecraft Lunar 1 became the first human-made object to escape Earth's gravity and enter orbit around the Sun. It missed the Moon, but it marked the beginning of interplanetary exploration. Only a few months later, Lunar 2 succeeded in striking the Moon's surface, and Lunar 3 took the first photographs of the far side, revealing terrain that no one on Earth had ever seen. These missions were crude by modern standards: limited power, analog instruments, slow data transmission, yet they transformed imagination into evidence. The Moon was no longer a distant light. It was a landscape with mountains, craters, and shadows. The next frontier was Venus, our nearest planetary neighbour. In 1962, NASA's Mariner 2 flew past Venus, becoming the first successful interplanetary probe. It revealed that the planet's thick clouds hid an atmosphere of carbon dioxide and a surface hot enough to melt lead. That single mission reshaped our understanding of planetary science. Until then, many had imagined Venus as a lush world, possibly home to life. Mariner 2 replaced that fantasy with fact. Venus was a furnace, a planet that had once been Earth-like, but had turned hostile through runaway greenhouse effects. A few years later, Mariner 4 flew by Mars, capturing the first close-up images of its surface. They showed a barren, cratered world, more like the Moon than the oasis some had hoped for. Yet those photographs, grainy and faint, were history's first real look at another planet. The moment they were transmitted back to Earth, humanity's mental map of the solar system changed forever. By the late 1960s and 70s, robotic exploration had become the vanguard of discovery. The Soviet Venera program sent multiple landers to Venus, some of which survived long enough to transmit images from the surface before being crushed and melted by the pressure and heat. Mariner 9 became the first spacecraft to orbit another planet, mapping Mars in detail and revealing vast canyons, volcanoes, and dried riverbeds. It showed that Mars had once been geologically active, perhaps even wet. The Pioneer missions ventured farther still, past Mars, toward Jupiter, and beyond. Each success extended the boundary of human knowledge without moving a single human body. Then came the Voyagers. Launched in 1977, Voyager 1 and Voyager 2 were designed to take advantage of a rare planetary alignment that occurs once every 176 years, allowing a spacecraft to use gravity assist to swing from one giant planet to the next. They were built to last a few years, but have now travelled for nearly half a century. Voyager 2 visited Jupiter, Saturn, Uranus, and Neptune, still the only probe to have encountered the latter two. Voyager 1, after completing its survey of Jupiter and Saturn, took a different path, one that would carry it out of the solar system entirely. Both probes carried scientific instruments to study magnetic fields, radiation, and solar winds, but they also carried something symbolic: the golden records, phonograph discs containing sounds and images from Earth, music, greetings in multiple languages, natural sounds like rain and thunder. It was an act of optimism, a message sent into the cosmic ocean in case someone someday might find it. Decades later, the Voyagers are still transmitting. Their power comes from the slow decay of plutonium, producing just enough electricity to run a few instruments and their radios. The signals they send back are faint, weaker than a whisper, billions of kilometers away, but still detectable. Voyager 1 is now more than 24 billion kilometers from Earth, moving through interstellar space. Its transmissions take over 22 hours to reach us. No human has ever travelled even 1,000th of that distance. The spacecraft continues to function, aging slowly in the cold, carrying with it the most distant presence of humanity in the universe. After the Voyagers came a new generation of explorers that stayed closer but dug deeper. The Galileo mission orbited Jupiter for 8 years, studying its moons and discovering evidence of subsurface oceans beneath Europa's ice. The Cassini spacecraft spent 13 years at Saturn, revealing its intricate rings, storm systems, and Titan's methane lakes. When its mission ended, Cassini plunged deliberately into Saturn's atmosphere to avoid contaminating any of its moons that might harbour life. Before it burned, it transmitted data until its signal was lost, a fitting conclusion to a mission that had expanded our understanding of an entire planetary system. Closer to home, Mars became a long-term target. Starting in the 1990s, orbiters and landers began a steady campaign of exploration that continues to this day. The Pathfinder mission, with its small rover Sojourner, proved that mobile surface exploration was possible. Spirit and Opportunity followed, each designed for 90 days of operation. Opportunity lasted almost 15 years. Curiosity and Perseverance continue to analyse rocks, soil and atmosphere, searching for traces of past habitability. Drones now fly above Martian terrain, mapping regions once too difficult to reach. Mars has become a world familiar to us, not through presence but through proxy. We have more detailed maps of its surface than of the deep oceans on Earth. Beyond the planets, New Horizons provided the first close-up view of Pluto in 2015, revealing a complex world with mountains of ice and a heart-shaped plain of nitrogen frost. Like the Voyagers before it, New Horizons continues its journey outward, now exploring the Kuiper Belt, the region of icy remnants at the edge of our solar system. Its mission demonstrates a new kind of endurance, a single spacecraft built by humans, exploring for decades across billions of kilometers. Each of these machines is a fragment of our collective curiosity, a way to extend perception beyond the limits of biology. They are patient, uncomplaining, and precise. They send us images that no eye could ever see firsthand, and through them, we've come to know the structure of our solar system, the storms of Jupiter, the rings of Saturn, the dry valleys of Mars, the glowing tails of comets. Through robotic explorers, we've learned what worlds beyond Earth are truly like, not as distant points of light, but as places with weather, chemistry, and history. They also teach us humility. The farther our machines travel, the more they remind us of how vast and silent the universe is. Each signal takes longer to arrive, each image comes from farther away, and eventually the delay becomes so great that the connection feels almost symbolic. The Voyagers, still moving outward, are beyond the heliopause, the point where the solar wind gives way to the interstellar medium. Beyond that line, the Sun is just another star among billions. The probes drift in darkness, still carrying their messages from Earth, still moving farther every second. They are for now the edge of our presence. The success of robotic exploration also redefined what exploration means. It's no longer limited to physical presence. Discovery can happen through data and distance. The probes don't bring samples home, they bring information, streams of numbers that turn into pictures, measurements and insights. They've shown us volcanoes erupting on Io, ice geysers on Enceladus, and blue sunsets on Mars. They've found planets orbiting distant stars by tracing tiny fluctuations in light. Through their sensors, we have already explored hundreds of worlds, even if no human foot has touched them. The patience of these missions contrasts sharply with the brevity of human spaceflight. While astronauts orbit for months, robotic explorers last for decades. They don't need air or food. They can wait through long years of darkness as they coast between planets. Their journeys stretch across generations. The engineers who launch them often retire or pass away long before the data stops coming. Each transmission, each discovery, is a collaboration between the living and the legacy of those who built the machine. In many ways, our robotic pioneers are the bridge between our imagination and our capabilities. They go ahead of us, proving that the void can be crossed, that the distances between worlds can be measured and that even the most hostile environments can be understood. When humans eventually follow, to Mars, to the outer moons, they will walk paths first mapped by these silent travellers. When the Voyagers finally stop transmitting, when their power fades and their signals fall silent, they will continue moving forever. They won't slow down or stop. They will drift through interstellar space, long after the sun has changed and Earth has evolved beyond recognition. Somewhere, countless years from now, they may pass close to another star. They carry no navigation, no destination, just momentum. A reminder that exploration doesn't end with presence. Sometimes it begins with a quiet machine, built by fragile hands, still moving outward, still carrying our curiosity beyond the edge of light. Our robotic pioneers are not replacements for human explorers. They are our pathfinders. They mark the trail, test the unknown, and report back across impossible distances. They remind us that while human travel is limited by endurance and cost, the urge to explore has no such boundary. Every signal they send home, every photograph they return, is another step outward. Proof that we're still reaching, still learning, still moving beyond the horizon, even if we're doing it through the patient eyes of our machines. When people talk about space, the first thing that slips away is scale. Numbers are easy to say, but impossible to feel. We can picture a mountain or an ocean because we've stood near them. We can imagine driving across a country, or even flying around the planet. But space refuses to fit into any frame we understand. Its distances aren't just large, they are beyond intuition. You can describe them, calculate them, express them in kilometers or light years, but the mind can't hold them. They exceed experience. They make language strain under their weight. Every journey we have ever made, from the first orbit to the farthest probe, has been only a first step across a vast, incomprehensible field. The moon, the farthest place humans have walked, lies just 1 light second away. Light, the fastest thing in the universe, the very limit of motion, takes a single second to reach it. That's 384,000 kilometers. The International Space Station orbits only 400 kilometers up, so light gets there in barely over a millisecond. But even that brief gap between ground and orbit defines our current human reach. To the Sun, the distance is 150 million kilometers, which means that every ray of sunlight that warms your skin left the Sun about 8 minutes ago. You're always seeing it in the past. When we speak of Mars, we move into minutes, not seconds. Depending on their positions in orbit, Earth and Mars can be 55 million kilometers apart at their closest, or more than 400 million at their farthest. A radio signal travelling at light speed can take between 3 and 20 minutes to cross that gap. That delay means every command sent to a rover on Mars must be planned hours in advance. By the time engineers receive a signal confirming success or failure, the event has already happened. Even communication, the simplest connection between explorer and home, begins to break down under the pressure of distance. Beyond Mars lies the asteroid belt, a region that looks crowded in diagrams but is mostly empty. The average separation between asteroids is hundreds of thousands of kilometers. A spacecraft passing through might never come close to a single one. Jupiter sits about 5 times farther from the Sun than Earth does, around 778 million kilometers away. Light takes 43 minutes to reach it. If you were standing on one of its moons, Earth would appear as a pale blue star in the dark, its details erased by distance. Saturn, at 1.4 billion kilometers, receives sunlight that left the Sun over an hour and a quarter earlier. By the time light touches the rings, the events that produced it are already history. Those numbers begin to drift out of reach even for scientists who work with them daily. It's one thing to read them, another to internalize them. At Saturn's distance, the warmth of the Sun has faded to less than 1% of what we feel on Earth. The outer planets, Uranus and Neptune, sit so far away that sunlight takes more than 2 and 4 hours, respectively, to arrive. Out there, darkness dominates. The solar system's edge, defined by the region where the sun's influence begins to fade, lies tens of billions of kilometers from Earth. Even our fastest spacecraft take decades to reach it. The Voyager 1 probe crossed that boundary in 2012. It had been travelling for 35 years at over 60,000 kilometers per hour. At that speed, a flight from New York to Tokyo would last less than 5 minutes. Yet, even moving that fast, Voyager took more than a generation to escape the heliosphere, the bubble carved in space by the solar wind. That's how large even our own neighbourhood is, and beyond that edge, the distances grow so extreme that our usual units lose meaning. Astronomers switch to light years. The distance light travels in a year, about 946 trillion kilometres. Proxima Centauri, the nearest star beyond our Sun, is 4.24 light-years away. In kilometres, that's about 40 trillion. If Voyager 1 kept its current speed, it would take roughly 70,000 years to reach it. The scale of that number dissolves in thought. 70,000 years ago, humans were painting on cave walls, hunting with stone tools, and sharing the planet with other hominin species. That's how far away our nearest neighbour truly is. Even imagining a spacecraft that could make that trip within a human lifetime pushes the limits of known physics. At these scales, the solar system itself becomes a tiny island in a black ocean. The Milky Way galaxy, which contains hundreds of billions of stars, spans about 100,000 light-years across. That means light, the ultimate traveller, takes 100 millennia to cross it from one side to the other. If you could somehow move at that speed, every moment would carry you past worlds, nebulae and clusters, yet you would still need 100,000 years to reach the other edge. And beyond our galaxy lie countless others, over 2 trillion by current estimates, each with its own billions of suns, planets and moons. The observable universe extends roughly 46 billion light-years in every direction. The word observable is important because there's more beyond that. Unreachable, not because we can't go there, but because the light from those regions hasn't had time to reach us since the universe began. To even attempt to visualize these distances, astronomers often use scales that compress everything into ratios. If Earth were the size of a marble, the Moon would be about 30 centimeters away. The Sun, on that same scale, would be 120 meters distant, more than a city block. The nearest star would sit over 8,000 kilometers away, farther than any airplane can travel without refueling. In this miniature cosmos, the space between objects dwarfs the objects themselves. That's the structure of reality, mostly emptiness, punctuated by brief islands of matter. This emptiness doesn't mean absence, it means scale. Even between planets, space isn't entirely void. There are dust particles, cosmic rays, solar wind, magnetic fields, all subtle traces of the universe's structure. But their density is so low that you could travel millions of kilometers without touching a single grain of dust. A cubic meter of interplanetary space might contain only a few atoms. Between stars it drops even lower. The distances are so great that for practical purposes they are absolute. Our current propulsion methods, chemical rockets, can move us between planets, but not between stars. The energy required increases exponentially with speed, and the fastest attainable velocities still fall far short of what's needed to cross even 1 light-year within a lifetime. When you think about these scales, you begin to understand how extraordinary even small journeys are. Sending a probe to Mars is like hitting a moving target hundreds of millions of kilometers away with perfect timing. Guiding a spacecraft to Jupiter or Saturn requires calculating trajectories years in advance, adjusting for the gravitational pull of multiple planets, and relying on engines that must function flawlessly after years of travel. Yet, we've done it. We've reached those worlds, orbited them, and sent back pictures that reveal details as fine as clouds and rings. Those successes remind us that even if the universe is vast, it is navigable, at least within our local region. The further you go, the more the concept of distance merges with the concept of time. Looking outward is the same as looking backward. The light from the moon is a second old. The light from the sun is 8 minutes old. The light from the Andromeda galaxy, our nearest large neighbour, left 2.5 million years ago. When we look at distant galaxies, we're seeing them as they were when humans didn't yet exist. The universe we observe is, in every direction, a history of light still travelling. We never see it as it is, only as it was. This combination of immensity and delay creates a strange kind of intimacy. Even though the stars are unreachable, their light reaches us freely. The photons that strike your eye on a clear night might have been travelling since long before the first humans walked upright. Every time you look up, you're connecting with something ancient. In that sense, the sky is both distant and immediate, unreachable yet present. Understanding these scales changes the meaning of exploration. We often imagine travel as movement from one place to another, but in space, movement itself becomes relative. Planets orbit, stars drift, galaxies rotate. Nothing is still. Even standing on Earth, you're already moving through space at tremendous speed, rotating with the planet, orbiting the Sun, and following the Sun's orbit around the Milky Way. Yet everything feels still because distance dilutes motion. Space is too large for our senses to perceive its dynamics directly. That's why comparisons help. If you could shrink the entire solar system, the Sun, and its outermost planet, Neptune, into the size of a coin, the nearest star would still be several kilometers away. If you could fly at the speed of a light, it would take 4 years to reach it. At airplane speeds, the same trip would take more than 50 million years. These are not just large numbers. They are limits that define what far truly means. Our robotic probes, moving faster than any other human-made objects, have crossed billions of kilometers, and yet, in cosmic terms, they have barely left home. They are still inside the neighbourhood of the Sun, still within a zone that light crosses in mere hours. The scale of the universe makes even our greatest achievements look small, but that smallness doesn't diminish them. It gives them meaning. Each step outward, no matter how tiny compared to the whole, represents a victory over the constraints of biology and gravity. When we ask how far we can travel in space right now, we're really asking where the boundary of possibility lies. The distances defy imagination, but imagination is precisely what keeps us moving. The measurements may be incomprehensible, but they also remind us why exploration matters. To cross even a fraction of those distances is to expand the range of life itself, and so we keep sending ships outward, probes, telescopes, and someday, people again, into the vastness that resists comprehension. The emptiness between worlds isn't just a barrier, it's an invitation, a measure of how much more there is to know. Space will always be too large for the human mind to contain, but that's what makes it worth reaching toward. Every number, every journey, every faint signal that returns from the dark is another proof that even distances that defy imagination can still be touched, one small step at a time. The idea of leaving Earth feels simple until you try to do it. The physics behind every launch, every orbit, and every attempt to go farther begins and ends with limitation. Gravity, mass, fuel, and energy form the boundaries of what's possible. We've learned to stretch those boundaries, to nudge them outward through clever engineering and endurance, but the laws themselves remain unbroken. They are the conditions of reality. The same physics that keeps us grounded also defines how far we can climb. At its core, space travel is about velocity. To leave the planet, a spacecraft must move fast enough to overcome Earth's gravity. The number that captures this is called escape velocity, about 11.2 kilometers per second, or roughly 40,000 kilometers per hour. It's not about pushing upward, but about moving fast enough sideways that gravity's pull curves you into orbit, instead of pulling you back down. Every mission, whether to orbit the moon or beyond, begins with this fight against gravity. Rockets are built to deliver that speed, but doing so takes enormous amounts of energy. The challenge isn't the distance, it's the exponential relationship between mass and fuel. The more fuel you carry, the heavier the rocket becomes. The heavier it becomes, the more fuel you need to lift that fuel. This loop, known as the tyranny of the rocket equation, is the fundamental constraint of spaceflight. For every kilogram of payload, a person, a machine, or a tool, you need dozens of kilograms of propellant. That's why most of a rocket's size is tank, not cargo. When you watch a launch, what you're really seeing is an enormous container of chemical energy burning itself away to move a tiny fraction of its own weight. A typical rocket sheds its stages as it climbs because each empty tank becomes dead weight. The first stage burns for just a few minutes, falls away, and crashes into the ocean or returns to land. The second stage ignites, taking over as the atmosphere thins. The final stage pushes the remaining payload into orbit or onto a trajectory toward another world. In the end, only a small capsule or probe survives the climb. The rest of the rocket is discarded. This is why every gram matters. Every screw, wire, and panel is weighed, optimized, and reconsidered. A few kilograms saved on Earth can mean thousands of kilometers gained in space. The physics of propulsion adds another layer of limitation. Chemical rockets, the kind we still use, work by burning fuel and expelling it at high speed through a nozzle. The faster the exhaust, the more efficient the thrust, but chemical reactions can only release so much energy. Even the best rocket fuels, like liquid hydrogen and oxygen, convert only a small fraction of their mass into kinetic energy. They are powerful but wasteful. Once the fuel is gone, the journey ends. The rocket equation doesn't just describe the difficulty of launch, it dictates how far we can go afterward. That's why interplanetary missions rely on careful trajectories instead of brute force. To reach Mars, a spacecraft doesn't fly straight toward it. It follows a curved path called a Hohmann transfer orbit, using the least energy possible to move from one orbit to another. Each launch window must be timed precisely, so that Mars is in the right position months later. Miss that window, and you either waste enormous fuel correcting your path or wait another 2 years for the next opportunity. Every journey through space is a balance between energy and patience. The physics doesn't allow shortcuts. Inside those boundaries, human ingenuity has found ways to push efficiency. Ion propulsion, for example, replaces chemical explosions with electric acceleration. Instead of burning fuel, an ion engine uses electricity to eject charged particles at extreme speeds. The thrust is tiny, about the weight of a sheet of paper resting on your hand, but it continues for months or years without stopping. Over time, that steady push builds remarkable velocity. Spacecraft like NASA's Dawn mission used ion propulsion to visit multiple asteroids, something impossible with chemical rockets alone. It's slow to start but efficient over long distances, a reminder that patience can substitute for brute strength. Yet even ion engines have their limits. They still rely on propellant, and they still can't approach anything close to the speed of light. The closer you get to that ultimate limit, the more energy you need. According to Einstein's theory of relativity, as an object accelerates, its mass effectively increases relative to the energy driving it. Reaching even a small fraction of light speed would require energy beyond anything humanity can produce. For interstellar travel, that's the wall we face. Not imagination, not technology, but energy. Time also becomes a limit. Every engine we know works within the lifespan of its builders. Chemical rockets can run for minutes. Ion thrusters can last for years. But travelling to another star at current speeds would take tens of thousands of years. That means no single generation could begin and end such a journey. Even if we could build a ship that lasts that long, we'd have to design systems capable of maintaining themselves for millennia. The problem isn't just propulsion, it's endurance, decay, and continuity. Closer to home, another limitation defines our reach: radiation. Beyond Earth's magnetic field, space is filled with charged particles from the Sun and cosmic rays from distant galaxies. These high-energy particles pass through metal, electronics, and even human tissue, damaging cells and equipment over time. On short missions, to the moon, for example, the exposure is manageable, but for months or years in deep space it becomes lethal. Shielding against radiation adds weight, which demands more fuel, which again amplifies the problem of mass. It's a chain of interlocking limits, each one reinforcing the others. Life support systems face similar constraints. Humans need air, water, and food, all of which must be carried or produced. A single astronaut consumes about 0.8 kilograms of oxygen and nearly 3 kilograms of water each day. Over months, those needs multiply into tons of supplies. Recycling systems can reclaim some resources. The International Space Station recycles nearly 90% of its water, but closed loops are never perfect. Some losses always occur, and resupply is impossible once you move beyond Earth's orbit. Long-term missions require systems that can maintain balance indefinitely, something we are only beginning to master. Thermodynamics introduces another boundary: heat. In space, there's no air to conduct it away, so every spacecraft must radiate its heat through panels that glow faintly in infrared. The more power a ship uses, for propulsion, life support, or communication, the more heat it must shed. This becomes another scaling problem. More power requires more radiators, which add more weight, which requires more power to move. Spacecraft design is a constant negotiation with physics, a compromise between what's desirable and what's possible. Even communication, something we take for granted, follows these limits. Radio waves spread and weaken as they travel. The signal from Voyager 1, transmitted by a 20-watt transmitter about the power of a refrigerator bulb, arrives at Earth's antennas 24 billion kilometers away, with less energy than a snowflake hitting the ground. To detect it, we use vast radio dishes and hours of processing. At interstellar distances, even light-speed communication would mean years or centuries of delay. Exploration beyond the solar system will not just be a matter of travel, it will mean isolation, with messages arriving long after they are sent. Every attempt to go farther is a negotiation with these limits. Faster travel requires more energy, but more energy creates more heat, more radiation, more structural stress. Larger ships offer redundancy but demand more fuel. Smaller ships are efficient but fragile. Every solution introduces a new problem. The miracle is not that we're constrained, but that we've managed to go as far as we have within those constraints. Human progress in space has never come from breaking the laws of physics, but from learning how to live within them creatively. The entire concept of orbital mechanics is built on that understanding, using gravity, momentum, and timing instead of fighting them. Spacecraft use gravity assists, swinging around planets to gain speed without burning fuel. This is not magic, it's precision. Each maneuver must be calculated years in advance, down to fractions of a second to catch the exact alignment that offers a free boost. These maneuvers have sent probes to Jupiter, Saturn, and beyond, piggybacking on gravity itself to cheat the limits of propulsion. We've also learned that limitation drives invention. The same problem that made rockets wasteful led to reusable boosters, which now land themselves for future flights. The weight constraints that make space travel difficult have pushed material science to produce lighter alloys, stronger composites, and more efficient systems. Every obstacle becomes a reason to innovate, to find new ways to work within the same physical laws that define us. The speed of light, the ultimate limit, is sometimes seen as an obstacle, but is also the constant that keeps the universe stable. Without it, causality would collapse. The same rule that stops us from reaching distant stars also allows stars and planets to exist at all. Limitation and possibility are inseparable. The laws that confine us are the same ones that make everything coherent. If there's a pattern in our history of exploration, it's that every boundary becomes a catalyst. The first rockets barely escaped the ground. Now we maintain stations in orbit and send robots beyond Neptune. The physics hasn't changed, only our precision has. We've learned to navigate within the rules, to bend them through understanding rather than defiance. That is the real engine of progress. When we talk about how far we can travel right now, what we're really describing is the sum of those limitations: fuel, mass, radiation, time, and energy. Each one defines the edge of our reach. Together they create a map of what's possible today and what might become possible tomorrow. The physics of limitation isn't the end of exploration, it's its foundation. It gives meaning to the effort. To move even a few kilometers farther into that vastness requires mastering forces that have existed since the universe began. So when rockets rise and disappear into the sky, what they carry isn't defiance of physics but cooperation with it. Each ascent is an acknowledgement that progress happens not by escaping limits, but by understanding them so deeply that they become tools. The universe sets the boundaries. We build within them. Every launch, every signal from a distant probe, every future ship that leaves orbit is proof that even within the strictest laws, there is room to move, slowly, precisely, and endlessly outward. Mars has always been more than a planet. It's a mirror, a small cold reflection of what Earth might become, and a destination that has pulled at human imagination for generations. When we think about the future of space travel, we inevitably end up there. It's the next logical step, the nearest world that feels almost reachable. For decades, engineers, scientists and dreamers have looked at its reddish light in the night sky and imagined walking on its surface. It's not fantasy anymore, but it's also not close. Mars is both near and impossibly far, a destination so familiar that we name its valleys and hills, yet so distant that no human has ever been within millions of kilometers of it. The distance between Earth and Mars changes constantly. Both planets orbit the Sun, but at different speeds and paths. When they align favourably, a moment called opposition, they're about 55 million kilometers apart. When they are on opposite sides of the Sun, the distance can stretch to more than 400 million. That gap isn't just space, it's time. It determines how long a journey would take, how much fuel would be needed, and how long astronauts would be away from Earth. Using current technology, a one-way trip would take between 6 and 9 months depending on the trajectory. There's no quick return, no rescue window. Once a spacecraft leaves Earth for Mars, it's committed to a journey through months of isolation and silence. We've been studying Mars closely for decades, but only through machines. Orbiters, landers, and rovers have turned what was once a distant point of light into a world we can describe in detail. We know its mountains, its canyons, its weather. We've seen its dust storms swell to cover the entire planet, its ice caps grow and shrink with the seasons, and its thin atmosphere shimmer with carbon dioxide frost. We've even heard its winds, faint and brittle, through the microphones on our rovers. Through those robotic eyes and ears, Mars feels almost within reach. But sending humans there remains one of the most complex challenges we've ever faced. Every factor that defines our limits comes into play at Mars. Distance, energy, time, radiation, gravity, and psychology all collide in a single problem. To send a crew there safely, we need to solve each one completely. The first challenge is propulsion. The same chemical rockets that carried us to the Moon can't efficiently carry enough fuel for a round trip to Mars. Engineers must plan careful trajectories, sometimes using multiple launches to assemble a spacecraft in orbit before departure. Even then, the journey is slow. The crew would spend months in microgravity, exposed to cosmic radiation and the mental strain of deep space isolation. The radiation problem is one of the hardest to solve. Earth's magnetic field protects us from most high-energy particles. Once outside that shield, astronauts are exposed to a steady flux of radiation that can damage cells and DNA. On short missions, to the Moon or the International Space Station, the exposure is manageable. but over months in deep space the dose accumulates. Shielding can reduce it, but shielding adds mass, and every kilogram of mass demands more fuel. It's a balance of safety and feasibility. Some designs propose using water tanks or fuel containers as radiation barriers, wrapping the living quarters in layers of hydrogen-rich material. Others suggest burying habitats beneath Martian soil once there, using the planet itself as protection. The trip isn't just about getting there, it's about staying there. Mars has an atmosphere, but it's thin, less than 1% the density of Earth's. It offers almost no protection from solar radiation or micrometeoroids. The air is mostly carbon dioxide, useless for breathing but potentially valuable as a resource. Future missions plan to use a process called in situ resource utilization, converting Martian CO2 into oxygen and methane fuel using electrochemical reactions. This approach, already demonstrated in small-scale tests, could allow crews to generate what they need rather than bringing everything from Earth. It's a step toward independence, a way to survive on a world that gives nothing freely. Gravity on Mars is about 38% of Earth's. It's enough to keep things anchored, but not enough to maintain bone and muscle strength long term. Prolonged exposure to reduced gravity leads to weakening of the body, and scientists don't yet know how reversible those effects are after years away. Life support systems must be closed and redundant, capable of recycling air and water indefinitely. Food production too becomes essential. Experiments on the International Space Station have shown that plants can grow in microgravity, but Mars offers additional challenges: lower light levels, toxic soil chemistry, and limited water. Yet, despite all these barriers, progress continues. Each of these problems has a potential solution, even if none are easy. The question is not whether humans can reach Mars, but when and how safely. Robotic missions have already prepared much of the groundwork. The orbiters map safe landing sites. The rovers measure radiation and study soil composition. They've found evidence that liquid water once flowed there, carving river valleys and filling ancient basins. They've detected minerals that form only in the presence of water, and in some areas, frozen reservoirs just below the surface. Mars, for all its desolation, was once active and possibly habitable. That possibility fuels the drive to visit it, not just to plant a flag, but to search for traces of life, past or present. Psychologically, a Mars mission would test endurance in ways we've never experienced. The crew would be completely isolated, unable to communicate in real time. Messages from Earth could take 20 minutes to arrive, and the same to return. That delay means no live conversations, no immediate help in emergencies. The astronauts would have to operate with autonomy, relying on pre-planned protocols and trust in their systems and one another. The duration, up to 3 years including travel and surface stay, would demand stability not just in technology, but in the human mind. On the International Space Station, astronauts can see Earth and talk to their families daily. On Mars, the view would be a pale blue dot, too far to touch, too distant to help. For all these reasons, Mars represents both the next step and the next barrier. It's close enough to be reachable with known physics, but far enough to expose every weakness in our systems. The risks are real, but the reward, extending human presence to another planet, is beyond measure. It would be the first time life from Earth has set foot on another world since the beginning of time. That fact alone carries immense weight. The first human footprints on Mars will not look like the Moon's. The soil is different. Fine, sticky dust that clings to everything. The sky is tinted pink from suspended particles. Gravity is light enough to make walking awkward, like slow motion. The silence will be total, broken only by the sound of breathing inside helmets and the hum of life support systems. When that moment comes, it will represent more than exploration. It will mean that Earth has extended itself, biologically, technologically, and psychologically, into the wider solar system. For now, we are still preparing. The upcoming Artemis missions aim to return humans to the Moon, not as an end, but as a rehearsal. Lunar missions will test habitats, equipment, and life support systems in an environment that's close enough for quick return, but harsh enough to serve as training. The Moon will become the proving ground for Mars. Each step taken there will be practice for the much longer leap outward. When we finally go, the journey will not be fast. It will begin with months of careful ascent, long coasting through the void, and a slow descent into the thin Martian air. The landing will be violent, friction turning to fire, then parachutes and thrusters fighting gravity in an alien sky. And when the dust settles and the engines go silent, the world will look unchanged. There will be no crowds, no noise, just a few distant cameras and the knowledge that something irreversible has happened. Humanity will have moved its boundary again. The first missions will likely be temporary, lasting only long enough to test equipment and gather data. But the goal is permanence. Bases, laboratories, greenhouses, communication relays. Each success will make the next step easier. Each setback will teach something crucial. Over time, the line between visiting and living will blur. Standing on that cold, quiet planet, an astronaut will be able to look up and see Earth as a star, a blue point among many. The distance will be millions of kilometers, but visible all the same. That view will change everything. Just as seeing Earth from orbit transformed how we think about our planet, seeing it from Mars will expand our sense of home. It will no longer be one world, but two. Fragile, connected, and alive across the void. The nearest shores of the cosmic ocean aren't across water, but across vacuum. Mars is that shoreline, the place where the dream of interplanetary life will first become real. The journey will be long and difficult, filled with risk and uncertainty, but it will happen. The trajectory is already set, and the preparations are already underway. Each new rover that lands, each test of propulsion, each successful life support trial moves us closer. When we finally arrive, it won't be a triumph of conquest, but of continuity. From firelight to starlight, from sails to rockets, from Earth to Mars, it will be the same human story repeating itself in a new setting. Exploration will continue as it always has, one step at a time into the unknown, with the horizon just ahead, waiting to be reached. The farthest machines ever made by human hands are already beyond the sun's influence, drifting in a place where the light from our star is no longer dominant, where space itself begins to belong to something else. These machines, the Voyagers, the Pioneers, and their few companions, are not large or flashy. They are small, metal bodies wrapped in gold foil, powered by decaying atoms, carrying the quiet hum of electricity across emptiness. They are the true explorers of interstellar space, and their journeys mark the outer boundary of everything our species has touched. When you think about what they've done, it's easy to forget how fragile they are. Voyager 1 and Voyager 2 were built in the 1970s, using technology less advanced than what now fits inside a pocket. Their memory storage could hold only a few images at a time, their cameras were mechanical, their computers primitive. And yet these same spacecraft have travelled farther than anything else humans have ever made, more than 20 billion kilometres from home and counting. They've gone beyond the planets, beyond the heliosphere, into the region where the sun's magnetic field and solar wind fade into the background of the galaxy. They are for now our farthest machines. The idea that they could still be functioning is almost unbelievable. After decades in flight, their power supplies are weakening, their instruments slowly shutting down one by one to conserve energy. But some continue to transmit faint signals. The radio waves they send are unimaginably weak. By the time they reach Earth, their strength is less than a trillionth of a watt. And yet our receivers still hear them, deciphering those whispers into data about temperature, radiation and magnetic fields far beyond the planets. Each signal that arrives is a message from the edge of the sun's reach, a confirmation that they're still there, still moving. Before they became distant symbols, they were working explorers. Voyager 1 flew past Jupiter and Saturn, revealing worlds of complexity that had only been dots of light before. It showed the swirling storms of Jupiter, the layered bands of its atmosphere, and the thin rings surrounding it. At Saturn, it discovered the intricate structure of its rings, billions of icy particles orbiting in perfect patterns, and took close images of Titan, a moon shrouded in haze. Voyager 2 followed a different path, visiting all four gas giants, Jupiter, Saturn, Uranus, and Neptune. It remains the only spacecraft ever to have seen the last two up close. At Uranus, it found a planet tilted so far on its side that its poles take turns facing the sun. At Neptune, it watched dark storms swirl across a cobalt blue atmosphere. After that, both Voyagers continued outward, passing beyond the known worlds into deep space. Their journey isn't fast by cosmic standards, but it's steady. Voyager 1 moves at about 17 kilometers per second relative to the Sun, enough to cover the distance from New York to Los Angeles in under 4 minutes. At that rate, it travels more than 500 million kilometers every year. Even so, it would take it more than 70,000 years to reach the nearest star. That gives a sense of how vast interstellar space truly is. The Voyagers are fast, but the distances ahead are overwhelming. They're racing through an ocean so wide that even at their speed, the stars hardly seem to move. What they've already shown us, though, is invaluable. Before them, no one knew exactly where the boundary of the solar system ended. The Sun's influence extends much farther than the orbit of Neptune. Its magnetic field and stream of charged particles, the solar wind, form a bubble around the solar system called the heliosphere. For decades, scientists theorized about its size and shape, but only the Voyagers could measure it directly. Around 2012, Voyager 1 crossed the heliopause, the point where the pressure of interstellar plasma balances against the solar wind. Beyond that line, the density of charged particles increased, and the direction of magnetic fields shifted. The spacecraft had left the Sun's domain. Voyager 2 followed in 2018, confirming the data. For the first time, instruments built on Earth were recording conditions in true interstellar space. These two craft aren't alone out there. The Pioneer 10 and 11 missions, launched earlier in the 1970s, also left the solar system, though they've fallen silent. Pioneer 10, the first to reach Jupiter, stopped transmitting in 2003, more than 12 billion kilometers away. Pioneer 11, which flew past Saturn, lost contact in 1995. Their signals are gone, but their momentum carries them onward. New Horizons, launched in 2006, joined this small fleet decades later. After visiting Pluto in 2015, it continued into the Kuiper Belt, the region of icy remnants beyond Neptune. It's still operating, studying distant objects and measuring the environment near the edge of the Sun's influence. One day, it too will pass into interstellar space, following the same long path into darkness. Each of these missions carries a small human signature. The Voyagers have the famous golden records, gold-plated copper discs containing sounds and images from Earth. They hold greetings in 55 languages, music from across cultures, and encoded photographs of people, animals, and landscapes. The Pioneers carry aluminum plaques engraved with figures of a man and a woman, the outline of our solar system, and the location of our Sun among nearby stars. These symbols aren't meant to be found anytime soon. The odds of another civilization encountering one of these craft are infinitesimal, but they serve a different purpose: to declare that, for the first time, life from one world built something that escaped its own star's gravity. They are both scientific instruments and monuments. In practical terms, these missions have already outlasted every prediction. Their power comes from radioisotope thermoelectric generators, devices that convert the heat from decaying plutonium into electricity. Each year, the energy output decreases as the plutonium cools. Engineers at NASA's Deep Space Network gradually turn off instruments to save power for the transmitters. Eventually, even those will fail, and the spacecraft will fall silent. When that happens, they will continue travelling, carrying their messages in silence. Long after every trace of their creators has vanished from Earth, these small ships will still be drifting between the stars, their trajectories defined by physics alone. If you could ride along with one of them, the view wouldn't change much from year to year. The stars would appear fixed, their movement imperceptible across human lifetimes. The sun would shrink to the brightness of a distant star surrounded by the faint outline of the Milky Way. There would be no noise, no vibration, no sensation of motion, just the slow, steady drift through a place that is almost entirely empty. The temperature would hover near absolute zero, the environment almost pure vacuum. Yet, even there, particles of gas and dust still exist, colliding with the spacecraft at rare intervals. In that endless silence, our farthest machines keep moving, carrying the sum of what we've learned and the trace of who we are. Their distance gives perspective. While the Voyagers move through interstellar space, the nearest star, Proxima Centauri, remains 4 light-years away. That's 40 trillion kilometers. At their current speed, they will never reach it in any time frame that matters to humanity. If we could somehow accelerate a future probe to 1/10 the speed of light, it would still take over 40 years to arrive. But that goal, distant as it is, has already begun to inspire new designs. Concepts like Breakthrough Starshot propose sending swarms of tiny laser-driven craft toward nearby stars, propelled by beams of light. These miniature probes, no larger than postage stamps, could reach speeds thousands of times greater than current spacecraft, crossing interstellar space within a human lifetime. They represent the next leap, the bridge between the machines we've already sent and the ones we might someday follow. For now, though, the Voyagers remain the farthest messengers. Their signals link us to the edge of the known. When those signals finally fade, there will be no fanfare, no final moment of contact. Just silence returning to a place that has been silent for billions of years. But the absence of communication won't mean the end of their journey. They will keep moving, endlessly outward, passing through the outer reaches of the Oort cloud, where comets drift in the dark and then beyond into the interstellar medium that fills the galaxy. The nearest stars will remain impossibly far, the light from their surfaces travelling years to reach us. But we've already made the first gesture. We've sent something across that gap, something built from curiosity and patience. The farthest machines are the first faint bridges between our sun and the countless others that fill the sky. They remind us that exploration doesn't always require presence. Sometimes it begins with a signal, a hum of data, a small golden record spinning quietly in the dark. And somewhere, billions of kilometers away, those signals are still travelling, expanding outward at light speed, crossing the space between stars. Long after the Voyagers themselves have gone cold, their radio waves will continue to move, carrying traces of their origin. In that sense, we've already reached the stars, not physically, but through the persistence of motion and the endurance of curiosity. The farthest machines have become part of the universe's background, drifting between suns, silent proof that life once looked up, wondered what lay beyond, and decided to find out. For all our progress, every machine that's ever left Earth still moves slowly. Even the fastest spacecraft we've built, the Voyagers, are crawling across the cosmic map at a pace that barely registers on a galactic scale. They will need tens of thousands of years to approach the nearest stars. The truth is simple and stubborn. We're trapped, for now, in a slow-motion universe. We can see everything, measure everything, and imagine anything. But our ability to travel remains bound by fuel, energy, and the limits of endurance. The physics is clear, but so is the desire to push beyond it. And so the question becomes, not whether faster ships can exist, but what kinds of patience and precision will be required to build them. If there's a single concept that defines our future in space, it's propulsion. Every dream of exploration, whether to Mars, the outer planets, or the stars, depends on how we move. The first rockets taught us how to escape gravity. The next generation will have to teach us how to escape time. That shift won't come through brute force or bigger engines, but through entirely new ways of thinking about motion. To travel across interplanetary or interstellar distances, we'll have to abandon the explosive chemical violence of today's rockets and turn instead to engines of light, plasma, and patience. Among the most promising ideas is the ion drive. It sounds like science fiction, but it already exists. Instead of burning fuel in rapid bursts, an ion thruster works by accelerating charged particles, ions, with electric fields. The thrust it produces is gentle, almost imperceptible, but continuous. Where chemical rockets burn out in minutes, ion engines can run for months or even years. That slow but steady acceleration adds up. A spacecraft using ion propulsion could eventually reach speeds far greater than any rocket relying on chemical combustion. Missions like NASA's Dawn, which visited the asteroids Vesta and Ceres, have already proven that the principle works. It's the difference between a sprint and a marathon, between a violent climb and a quiet glide through the dark. But even ion propulsion has limits. It still needs propellant, and the rate of acceleration, though steady, is small. To reach other planets faster, or to move beyond the solar system, engineers and physicists are exploring ideas that sound almost poetic in their simplicity, using light itself as a means of travel. Light has no mass, yet it carries momentum. When photons strike a surface, they exert pressure, tiny but measurable. In the vacuum of space, where resistance is almost non-existent, even the faintest push can accumulate. This is the foundation of solar sails. A solar sail is exactly what the name implies: a thin, reflective sheet designed to catch sunlight, the way a traditional sail catches wind. The force is weak but constant. Over time, a sail several hundred meters wide could accelerate a small spacecraft to thousands of kilometers per second, faster than any chemical rocket could ever achieve. The first test of this idea came from the Icarus mission, launched by Japan in 2010. It unfurled a sail thinner than a human hair, measuring about 20 meters across, and successfully demonstrated that sunlight alone could alter its course. Since then, smaller missions like LightSail 2 have refined the concept, proving that light pressure can indeed serve as a method of propulsion. What makes solar sailing unique is that it turns space itself into a fuel source. There's no need to carry propellant, no tanks to refill, no engines to ignite. The only limit is how long the sail can survive, and how precisely it can be controlled. The larger the sail, the greater the acceleration, but also the greater the risk. A sail hundreds of meters wide must remain perfectly oriented while resisting micrometeoroids, temperature extremes and radiation. The slightest misalignment can send it drifting off course. Still, the elegance of the concept has captivated scientists and dreamers alike. It represents a shift in philosophy. Instead of fighting against nature, we would be cooperating with it, using the universe's most abundant resource, light, as a current to ride upon. Solar sails, though powerful over long distances, are limited by the strength of sunlight. As a spacecraft moves away from the sun, the light weakens and the force decreases. Beyond the outer planets, sunlight becomes too faint to be useful. To overcome that, some proposals suggest using artificial light instead. Powerful lasers fired from Earth or from orbit to push sails across interstellar space. The idea, known as laser propulsion, could, in theory, accelerate tiny spacecraft to a significant fraction of light speed. Projects like Breakthrough Starshot, proposed by physicist Stephen Hawking and investor Yuri Milner, envision sending fleets of gram-sized probes attached to reflective sails. A ground-based laser array, concentrated into a narrow beam, would accelerate them to 1/5 the speed of light in minutes. At that velocity, they could reach the nearest star, Proxima Centauri, in just over 20 years. Such missions would mark a profound shift in exploration. Instead of building massive ships carrying people and fuel, we might first send swarms of miniature machines, tiny emissaries equipped with cameras, sensors and communication systems. They wouldn't carry passengers or return samples. They would send back data, flashes of information travelling at light speed across the void. They would be our first step into true interstellar space, made possible not by size or strength, but by precision and scale. Thousands of these small craft could be launched, knowing that even if most failed, a few might survive the journey. It's an approach based on patience and redundancy, not speed or spectacle. Beyond light and plasma, other propulsion concepts push the boundaries of what might one day be possible. Nuclear thermal rockets, for instance, could provide much greater efficiency than chemical engines by heating hydrogen with a nuclear reactor and expelling it at high velocity. They would allow faster travel to Mars, cutting the journey to a few months instead of nearly a year. Nuclear electric propulsion would go further, using reactor power to drive ion or plasma engines continuously for years. These technologies are heavy, complex and politically sensitive, but their potential is enormous. They represent a bridge between the limitations of today and the ambitions of tomorrow. Further still lie theoretical concepts, ideas that stretch the imagination but remain grounded in physics. One is fusion propulsion, which would harness the same reactions that power stars. By fusing light atomic nuclei like hydrogen into helium, enormous amounts of energy could be released, far more than any chemical reaction. A fusion engine could, in theory, sustain acceleration for months, achieving speeds that might make interstellar travel within a human lifetime conceivable. Several experimental designs exist, such as the Daedalus concept from the British Interplanetary Society, proposed in the 1970s. It envisioned a two-stage spacecraft propelled by fusion pellets ignited by electron beams. It would travel at 12% of light speed and reach Barnard's star in 50 years. Though the technology to build such an engine doesn't yet exist, the idea remains one of the most detailed blueprints for reaching the stars without violating physical laws. Then there are even more ambitious ideas. Antimatter propulsion, for instance. When matter and antimatter collide, they annihilate each other, releasing energy with perfect efficiency. 1 gram of antimatter reacting with 1 gram of matter would produce as much energy as 20,000 tons of TNT. If we could harness even a fraction of that power safely, we could reach unprecedented speeds. But antimatter is extraordinarily difficult to produce and store. Every particle must be contained by magnetic fields, isolated from contact with ordinary matter. The total amount of antimatter ever created by humans could barely fuel a light bulb for a few minutes. For now, it remains more of a symbol than a solution, a reminder that the ultimate sources of energy lie far beyond our current reach. Some concepts move beyond propulsion altogether and explore the geometry of space itself. The most famous is the idea of the warp drive, based on a solution to Einstein's field equations proposed by physicist Miguel Alcubierre in 1994. It suggests that space could be compressed in front of a spacecraft and expanded behind it, allowing the ship to move faster than light relative to distant objects without locally breaking the speed limit. In essence, it would surf a wave of warped space-time. The mathematics works in principle, but the energy required, involving exotic forms of matter with negative density, is far beyond anything achievable today. Whether such a system could ever exist remains uncertain, but the idea has value even as theory. It forces us to ask whether distance itself is the problem, or whether the structure of space could one day become the solution. Even if those technologies remain centuries away, the path toward them is being laid now. Every advancement in materials science, miniaturization, and energy storage brings the dream closer. The spacecraft of the near future won't look like the heavy, segmented rockets of the past. They'll be modular, autonomous, and intelligent. Artificial intelligence will handle navigation, course correction, and repair without waiting for instructions from Earth. Solar and nuclear power will feed engines that never truly shut off. Instead of short missions defined by fuel limits, exploration will become a continuous process. Ships moving outward slowly, steadily, almost organically, expanding the boundary of human presence year by year. This vision requires patience, not only in travel but in perspective. The distances between stars are so vast that even our fastest machines will take centuries or millennia to cross them. The explorers who design and launch these ships will never see their destinations. They will send them into the dark knowing that the results, the signals, the discoveries, will reach people far in the future. It's a new kind of exploration, one that demands trust across generations. The human story has always involved planting seeds for descendants to harvest. Interstellar travel will extend that pattern into cosmic time. The idea of patience as propulsion might seem poetic, but it's deeply practical. The universe doesn't reward haste, it rewards endurance. The same slow processes that built stars and planets operate in us too. Evolution, discovery and progress happen across spans too long to witness in full. The ships of light and patience reflect that truth. They are not weapons of speed, but instruments of persistence. They will move forward not in leaps, but in continuous, deliberate motion, carrying with them the quiet hum of civilization's curiosity. The most remarkable thing about these future ships isn't their engines, but their purpose. They exist to extend awareness. Every meter they cross, every bit of data they send home, expands the boundary of what is known. They turn empty distance into connection. That's what exploration has always been. The conversion of the unknown into the understood, one small increment at a time. Whether driven by sunlight, plasma, or nuclear fire, every future ship will share that same intent. In time, some of these ideas will move from concept to reality. Solar sails will grow larger, ion engines more powerful, nuclear propulsion safer and more efficient. Each generation will push a little farther. There will be accidents, failures, and decades where progress feels invisible, but the trajectory will continue outward. Humanity has never truly stopped moving forward. It only pauses between bursts of invention. When the first of these ships begins its long journey toward another star, it won't carry passengers. It will carry proof that we can think beyond our lifetimes, that we can act with a patience matching the scale of the universe itself. The ships of light and patience will not end exploration. They will redefine it. They will travel silently, powered by nothing more than the laws of physics and the endurance of design. They will move through darkness without hurry, guided by the same principle that has always driven us, that knowing what lies beyond is worth the time it takes to find out. And when they finally reach their destinations, whether that takes decades or centuries, they will carry with them not just instruments, but the memory of a species that learned how to wait. Distance is a word that seems simple until you start to live inside its meaning. On maps, it's measured cleanly, marked in kilometers, drawn as neat lines between one place and another. In life and in space, it becomes something else. A quiet weight that stretches across time, emotion and memory. We think of distance as something to conquer, something that can be closed with speed or cleverness. But the farther we travel beyond Earth, the more it begins to feel like a condition rather than a challenge, an inseparable part of existence itself. Space has always been there, not waiting for us, not resisting us, but simply being vast. We're the ones who had to learn what that vastness really meant. When people first saw Earth from orbit, the scale of the universe began to take on a new kind of intimacy. From above, the planet looked small and self-contained, wrapped in its thin blue skin of atmosphere, hanging in a black field of nothing. From that vantage point, everything human, every city, every war, every life, was hidden within that fragile film. It was a revelation of beauty, but also of separation. There was no up or down, no near or far, just a sphere floating alone. That view was our first lesson in the quiet truth of distance. That even home is already isolated, already surrounded by unreachable space. For those who have gone farther, to the moon, to to orbit. The silence that follows distance is absolute. Communication continues, but the delay begins to creep in. A second, 2 seconds, then more. The farther you go, the slower home seems to respond. The intimacy of connection stretches thin. A voice that once answered instantly becomes a message that takes time to arrive. By the time a reply returns, the world that sent it may already have changed. The simple act of speaking becomes an echo, a rhythm of waiting. This is the first thing distance teaches, that it changes not only where you are but how you exist in relation to everything else. In orbit, distance is visible but deceptive. Astronauts can see the entire planet below, every continent and cloud system in one glance, yet they can't touch any of it. The sight of home fills their windows, but it's unreachable, like a photograph you can never step into. On the moon, the effect deepens. Earth becomes a light in the black sky, distant but constant. It looks serene, perfect, and small. Small enough to be covered by a thumb. For those who stood there, the most striking part wasn't the moon's barrenness, but Earth's fullness. The distance between them was both infinite and immediate. One world so alive, the other so silent. When the Voyagers sent back their final images before their cameras were turned off, one of those photographs, the pale blue dot, became a kind of mirror for our species. From billions of kilometers away, Earth was just a fleck of light caught in a sunbeam. Every history, every language, every joy and loss, all condensed into a single pixel. It wasn't just perspective, it was truth. Distance had stripped everything away except scale. We are small, not metaphorically but physically. Even our greatest distances, our most daring journeys, vanish in the cosmic measurement. And yet, in that smallness lies something profound. That dot contains everything we've ever known, everything we've ever loved. The farther away you see it, the more fragile and remarkable it becomes. Distance doesn't erase meaning, it defines it. The reason the pale blue dot image moves people isn't because it makes Earth seem insignificant, but because it makes it visible as a whole. It's the same feeling that explorers have always known, standing on mountains or crossing oceans. To be far away is to understand closeness differently. In space, that feeling becomes literal. Every kilometre out makes home sharper, clearer, more precious. The blackness surrounding Earth isn't hostile, it's context. It's the frame that makes the light visible. The physics of space reinforces that truth. The farther something is, the longer its light takes to reach us. Everything we see in the sky is already gone from the present moment. The stars overhead are ancient photographs still developing in our eyes. The Andromeda Galaxy, visible on a clear night, appears as it was 2.5 million years ago. The universe, in that sense, is a collection of distances masquerading as moments. We live surrounded by the past, bathed in light that left its sources long before humans existed. The act of looking outward is always an act of looking backward. That relationship between time and distance changes how exploration feels. When a spacecraft travels to another planet, it doesn't just move through space, it moves into a kind of delay. Every message it sends home is a fragment of the past. For the people operating it, control becomes prediction, communication becomes patience. The space between signal and response grows wider until control is no longer possible. The farther we go, the more we have to trust what we've built to act on its own. Distance demands autonomy. It asks us to design machines, and eventually people, who can think and survive without waiting for instructions. For humans, that separation will be more than technological. It will be emotional. To leave Earth for years, to see it shrink to a dot, to know that every voice from home will come delayed and faint, that will redefine loneliness. The first crews to Mars will experience it. At their farthest point, radio signals will take up to 20 minutes to travel one way. That means no conversation, only messages sent into the dark with the hope of a future reply. The psychological effects are unknown. We've never lived that far from other people before. Even when explorers crossed oceans, they were still under the same sky, breathing the same air. Mars will break that pattern. For the first time, human beings will know what it means to be truly separate. But separation isn't only loss. Distance creates clarity. It allows perspective to form, both literal and philosophical. When astronauts return from space, many describe something called the overview effect, a shift in perception that comes from seeing Earth as a single borderless system. It's not an idea that can be taught, it must be felt. From above, there are no nations, no boundaries, only the delicate swirl of weather and light. Distance reveals unity by erasing proximity. It shows how artificial our divisions are, how deeply connected everything really is. That revelation doesn't fade easily. Once seen, it stays with them. A quiet understanding that Earth is not a collection of places but one living world. There's another kind of distance, though, the one we create between ourselves and what we explore. Space, by its nature, humbles the human sense of importance. We can send machines billions of kilometers away, but we can't change the fact that our reach is tiny compared to the scale around us. For some, that realization feels diminishing. For others, it's freeing. It removes the illusion that the universe revolves around us. Instead, it reminds us that existence is shared. Every atom on Earth came from the same cosmic processes that built the stars. The distance between us and them is not separation, it's ancestry. On Earth, distance can mean disconnection, a friend far away, a voice you can't reach. In space, distance becomes something else, the medium through which connection happens. Every photograph sent back from Mars, every data stream from a distant probe travels through billions of kilometers of nothingness. That emptiness doesn't block the message, it carries it. Space itself becomes the bridge. The silence between worlds is not empty in the way we imagine. It's full of invisible pathways, filled with the faint whispers of communication, signals crossing decades of travel. The same vacuum that isolates us also binds us through light and radio. This paradox, that distance separates and connects at the same time, sits at the heart of space exploration. The farther we go, the more we understand how bound we are to what we've left behind. Every spacecraft that leaves Earth carries its birthplace in its materials and its programming. Every astronaut who steps beyond orbit carries the language, memories, and culture of home. Even in the most distant places, we remain reflections of where we came from. Space doesn't erase identity. It magnifies it. If there's a quiet truth in all of this, it's that distance is not something to conquer. It's something to inhabit. The universe isn't arranged for convenience. It doesn't owe us proximity or speed. But within its vastness, there is room for everything, for movement, for stillness, for thought. The scale of space invites humility, not despair. It tells us that even the smallest motion outward, even the slowest signal sent, is an act of courage. When we send a probe beyond the heliosphere, when we plan for journeys that will outlast our lives, we're not trying to erase distance, we're learning to coexist with it. That coexistence is what defines the future of exploration. As technology improves, we will move farther and faster, but we'll also grow more aware of what we can't change. The speed of light will still govern communication. The laws of motion will still dictate travel. The space between stars will still stretch longer than lifetimes. Progress won't mean defeating those facts. It will mean building within them, learning to see beauty in slowness, meaning in waiting, connection in separation. The quiet truth of distance is that it's permanent, but not empty. It's the framework of everything that exists. Even on Earth, this lesson applies. The light from the sun takes 8 minutes to reach us. Every sunrise we watch is already history. The stars we see each night are older than our species. We live constantly in the presence of delay. surrounded by light that left its source long ago. Distance isn't just a property of space, it's part of time itself. Everything we see, everything we experience, arrives slightly late. The universe is always a little older than it looks. That understanding changes how exploration feels. It becomes less about arrival and more about relationship. Every step outward is part of a dialogue with time and space, a slow, deliberate exchange between what is near and what is far. The spacecraft we launch are our words spoken into that silence, and the data they return are the universe's replies. The conversation is vast, but it continues. Even when signals fade and machines go dark, the motion remains. Distance becomes the ongoing record of our attempt to understand. The truth of distance, then, is not loneliness. It's continuity. It's the reason light can travel, the reason orbits hold, the reason we can look up and see the past. It's the medium of existence. Every time we measure it, we're not calculating separation, we're tracing connection. The farther we look, the more we realize that everything, from atoms to galaxies, is linked by invisible threads stretched across immeasurable space. The universe is not empty between the stars, it's stitched together by gravity, energy, and time. For those who travel, or who will someday travel beyond Earth, that truth will be both comfort and challenge. The silence will be deep, the waiting long, the sense of distance overwhelming. But within that vastness, they'll carry the same connection that binds all explorers, the knowledge that even across billions of kilometers, even across light years of delay, they are still part of something continuous. The signals they send, the paths they trace, will all flow back eventually, weaving new threads across the same old space. Distance will always remain, a constant, quiet reminder of scale. But it will also always hold meaning. It shows us where we are and by extension who we are. We are the ones who measure, who reach, who send, who wait. We are the species that learned to live in a universe too large to comprehend and still found a way to belong to it. The quiet truth of distance is that it defines the boundaries of our reality, but it also gives us the space to imagine beyond them. It is both separation and possibility, silence and story. It is, and always will be, the backdrop against which every human act of exploration takes place. If you could step back far enough to see everything at once, every orbit, every ship, every light still moving across the night, you would find yourself at the centre of it all, not because of scale, but because of perspective. You are here, right now, on a planet that has travelled billions of times around its star, listening to the slow hum of the universe. Every distance we've crossed, every dream we've pursued into the dark begins from the same place, from where you are sitting, breathing, watching, wondering. The story of how far we can travel in space isn't only about rockets or engines or physics. It's about that curiosity, the quiet impulse to look up and imagine what might be waiting beyond sight. This moment, you, here, now, is part of that same trajectory. Every question about distance, every thought about how far we can go exist because something in the human mind refuses to accept stillness as enough. Long before rockets, before telescopes, before the language to describe the stars, people stared into the night sky and felt the same mix of fear and awe. They didn't know what they were seeing, but they understood that the lights above were unreachable and therefore eternal. That feeling, the tension between wonder and distance, is what drives everything we do in space. You could say that exploration begins at the edge of comfort, but really it begins in awareness. The realization that the ground you stand on is moving through space, that every second carries you thousands of kilometers through the cosmos, changes the idea of travel itself. You're already moving, around the planet, around the sun, around the center of the Milky Way. Even sitting still, you are in motion. The engines of Earth never stop, and neither does the curiosity that follows them. When you look up tonight, the stars will seem still, but they're not. Each one is racing through the galaxy, just like the sun, just like the spacecraft that leave Earth and drift outward. Some are approaching us, others are fleeing. Their light crosses unimaginable distances before it reaches your eyes, carrying information older than humanity. You're seeing not where they are, but where they were. Every time you look into the sky, you're looking into history, the deep, patient record of time written in light. That means that every star you see is a conversation already halfway over, its final word still arriving across the dark. You, right now, are part of that conversation. The same atoms that make up your body were forged in the cores of ancient stars. The calcium in your bones, the iron in your blood, the carbon that shapes every cell. All of it was born in the fusion furnaces of suns that lived and died long before Earth existed. You are, quite literally, a piece of the cosmos that learned to look back at itself. That's not metaphor, it's physics. The distance between stars is not just a number. It's the space across which you were assembled. Every breath you take is part of the same cycle of matter and energy that began with the birth of the universe. When we talk about how far we can travel in space, we usually think of ships, probes, and propulsion. But you've already travelled farther than any spacecraft will ever go. The elements that became you began their journey more than 13 billion years ago, when the first stars formed. They have moved through explosions, clouds, and collisions before finding their way into your body. In that sense, your existence is the universe's most complete form of travel. Matter that began as stardust, coalesced into life, and developed awareness of the journey itself. There's something grounding in realizing that. The universe is enormous, but it's not foreign. It's home. Every particle of your body is made of the same material that fills the galaxies. You're not separate from space. You are an expression of it, temporarily shaped into thought and motion. When we send machines outward, when we dream of distant stars, we're not leaving home. We're exploring another room in the same vast house we've always lived in. Still, it's easy to feel small when you think about the distances involved. The trillions of kilometers between stars, the billions of years between beginnings and endings. But smallness is not insignificance, it's precision. It means we exist at a scale where perception is possible, where time moves slowly enough for life to notice itself. The stars may burn for millions of years, but they don't wonder what they are. You do. That ability to ask, to listen, to look outward, even knowing how far away everything is. That's what makes being here meaningful. Think for a moment about everything that's been built just to help us see farther. The telescopes orbiting Earth, the probes still whispering from beyond Neptune, the stations that circle above our heads. They are extensions of the same desire that makes you pause and look at the night sky. Each one of them carries a part of that same curiosity outward, turning questions into data, into understanding, into more questions. The technology changes, the scale increases, but the motivation remains ancient. And even as those machines travel outward, the act of listening inward continues. Every photograph sent from Mars, every image of a distant galaxy, every signal caught from a spacecraft decades after launch, all of it returns here, to this planet, to people watching and thinking. The loop is never broken. Exploration is not escape, it's reflection. Space travel has never been about leaving Earth behind, it's about seeing it more clearly from afar. The farther we go, the more we understand how much we belong to the place we started from. There's a moment in every mission when the distance becomes too great, when signals take hours to arrive, when the spacecraft passes beyond the reach of direct control. At that point, everything depends on what was built, what was planned, what was trusted. The ship continues on its own, guided by physics, carrying with it the last commands from home. In that way, every spacecraft becomes a kind of metaphor for human life, launched with purpose, shaped by those who built it, and eventually continuing on into silence, carrying what it has learned. And even after the signal fades, the path it carved through space remains, invisible but real. The motion endures. You, here, now, are at the receiving end of those signals. When you think about the farthest machines, about the time it takes for light to reach your eyes, about the decades of waiting that go into every photograph from another world, you are participating in that same patience. You are part of the chain that connects launch to understanding. Every time you wonder what it must feel like to stand on another planet, to see the sun as a faint star, you're continuing the mission in thought. The exploration doesn't stop at the edge of the atmosphere. It happens here too, in the mind that imagines what's out there. All exploration returns to stillness eventually. After the calculations and the noise, after the engines and transmissions, there comes a point where everything quiets. You're left with the simple fact that we are a small species on a small planet, surrounded by vastness and somehow aware of it. That awareness is the miracle. It doesn't need grandeur or victory to matter. Just knowing that we exist within something so immense and still find meaning in it is enough. The distances between worlds will always be huge, the time to cross them immense, but they don't make us isolated. They make us part of something larger. Every atom, every beam of light, every sound, every life, all of it is part of the same ongoing motion. You, listening to this, are as much a part of space as the stars themselves. The only difference is that you can recognize it. You can look up and see your own origin shining back at you. So when the night comes and the sky begins to fill with its slow, steady pattern of light, take a moment before you drift off. Imagine where those lights come from, the centuries they've travelled, the energy that began in a sun and ended in your eyes. Think of the ships still moving through that darkness, their signals still crossing the void. Think of the earth beneath you, spinning quietly, carrying everything you know. And then think of yourself, breathing still and present, part of the same motion. The story of how far we can travel in space isn't finished. It never will be. Every generation will add a little more distance, a little more understanding. But even as we move outward, the centre of that story stays the same. It's you and everyone like you, looking upward, feeling the quiet pull of curiosity. You don't need to travel billions of kilometres to touch the universe. You're already in it. You always have been. The machines will go on. The stars will keep shining. The distances will remain. And somewhere in all of that, you are here, not apart from it, but within it. Part of the same vast, patient story that began long before words and will continue long after they're gone. The universe isn't somewhere else, it's this, it's now, it's you.